Hello, people.
Afternoon.
Good afternoon.
How are you?
Okay.
Got
Hey,
a-
Mike.
Good morning.
in a different setting than usual. Or I was in New Jersey, now I'm in Philadelphia.
Okay.
Are you a New Jersey or Philadelphia native?
New Jersey.
Oh, but your family lives in Philadelphia now.
Well, kind of the opposite way around. Like my family still lives in New Jersey.
Oh,
You know what W.C. Fields said?
What?
On the whole, I'd rather be in Philadelphia.
No, he said, I'd rather be here than in Philadelphia, referring to his grave.
He also said, water, never touch the stuff. Fish fucking it.
Oh, my mother didn't raise me to listen to language like that. Who said that foul word? Who is that? Victor? Who is this? Stop laughing, David. Not that funny.
All right, let's give it a couple more minutes just in case anybody's running a little bit.
Can I ask you a question? Because there's very few people, and so we're not
Yeah.
ready. I get the sense that this is only the second one I've taken part in. I had trouble getting into the second session for some reason, technical issue, but I get the sense that there's a subtext to everything that you are talking about. And I think, and that subtext to me that is implied to me is quantum computing in particular, and that a lot of the issues that you're addressing, you're directly or indirectly addressing the underpinnings of quantum computing. Am I right in saying that?
Sure, yeah. I mean, I think that like when I came to quantum physics, it was from, in some ways, like a computer programming background.
Mm-hmm.
And so, you know, my first exposure to quantum stuff wasn't so much solving differential equations, and it was like learning how to play around with, you know, vectors and matrices and qubits. And so I definitely think in a sort of quantum computational way.
Was anybody at the Quantum Appalooza, which just ended? You know, Terrell's, because I think Terrell is going to be coming to this one.
Yeah, it was, Michael. I saw you there, so I thought, okay, good. I didn't miss the New York quantum group today. I saw you popping in there briefly.
Yeah, I actually I was pissed off with Terrell, but I should apologize because he didn't give us the right link.
Oh.
And then I finally was able to get in halfway through, but I mean, I already knew that stuff anyway.
Yeah, they started over.
Gates. I'm sorry?
They started over. They had, she had like 8 of them out there already. And then she started back at number 1 for some reason. So I think she's starting up new. Like the Microsoft Reactor from like all over the world is kind of dialed in. So now there's 70 participants instead of 20. So she's gotten more people. I think she's starting fresh with a new audience.
Interesting.
Was she presenting from China? Is she in China? Because the time she gave was like the other side of the world. Where is
she said, I don't know. She said 9:30. I know she's with Microsoft, but yeah, I don't know where she's based out of.
Yeah. She's based in Asia. She's not based in the Western Hemisphere.
Yeah, what was the main topic of discussion? I wasn't there.
It was an introduction to quantum computing. You know, if you know what the most complicated thing she presented was the Hadamard gate. I think we all probably know what that is.
We're going to talk about a little, it's going to come up today.
Yeah. Well, that's why we're here.
But yeah, well, you know, when I discovered that paper about wormholes that, you know, the first couple meetings were based on, you know, it was like, you know, they were breaking down the wormhole algorithms, you know, that people have been developing for years, like in terms of qubits and stuff like that, which, you know, that was sort of the proximal
Do you believe in wormholes? I mean, they've been proven to be impossible in so many different ways.
Yeah, well, I mean, so far as I understand it, in general relativity, classical general relativity, they are not traversable.
Right, they're not traversable. But basically, it's an extension of
In the case, though,
entanglement.
it's fairly convincing that something's going on.
Well, it's entanglement. It's entanglement between two black holes that were already entangled before they became black holes. So, but the whole thing about a wormhole is kind of stretching it.
Well, yeah. So, I mean, like the deep question is like, how, you have entanglement and then you have, geometrical connectivity. And, there's this suggestion that.
But there's geometry, which is math, and then there's physics. And unfortunately today, instead of traditionally where physics led math, now math is leading physics. Math is trying to make predictions about the physical universe. Like string theory is the classic example now, which is ridiculous. If there's no empirical evidence for something, then it's just math.
Sure.
It's not the real world.
There's some, you might be right. At the same time, I mean, we wouldn't be anywhere near where we are today without stuff like string theory.
No, and string theory is a worthwhile pursuit. I grant it, because if nothing else, it facilitates computational things. But to just say, well, because the math says this is so, therefore it's a physical reality. That's where's the empirical evidence?
Yeah, math is about, some rules. He's like, here's some rules. You want to know what the consequences are. You want to explore the space of possible rules.
Right.
And then physics is about comparing it to experience. I mean,
well, physics is rules too. But the thing is, physics has to be explained by math, but math doesn't automatically equate to a physical reality.
It's true. I agree with you, but then, at a deeper metaphysical level, one has to wonder, like, unless you're a mathematical Platonist, you have
What
to.
What did Woody Allen say about metaphysics? Do you know who Woody Allen was? When he was caught cheating on his final exam, he said, "I was just looking into my classmates' metaphysical reality," or some.
Yeah. I know what the quote you're talking about.
No, I mean, if you've got if physics is that dependent on mathematical logic, so that the mathematical logic seems to really become a mathematical formalism or a mathematical mysticism, which I think it becomes in a lot of theoretical physics, and you're not able to move from a mathematical logic to logic, scientific logic, philosophical logic, that critiques it, that frames it, that perhaps limits, if you have 11 theories of the black hole and you have 11 different mathematical models, well, obviously, either all of them are wrong or most of them are wrong. And yet, the very fact that they're based on mathematical models, they're somehow anointed as possibilities that we should unceasingly entertain. And then, but if you can't move beyond that into the realm of, logic, scientific logic, philosophical logic that you can apply to it, and determine whether it even is a physical possibility in spite of what the math is telling you, then I don't really think you're dealing in the realm of science. You're closer to the realm of sort of medieval theology, where you debate how many seraphs can dance on the head of a pin.
Who is that Victor speaking?
Of course it is.
But because we can't see you. We can't see you. I heard you're a really good looking guy. Why didn't you turn on the video? Now look, we've reached a point where we haven't really discovered, there haven't been any breakthroughs in physical science like there have been through most of the 20th century. So now they're using math to attempt breakthroughs, but sure, the math is valid, but it doesn't necessarily equate to the real universe. And this is the problem primarily with string theory. But don't go to Columbia University and tell anybody in their physics department what I just said, because they'll
I mean, I
put a
see
contract out on your life.
yeah, right.
They've got a professional vested interest in promoting string theory. And guess what? There's no women on the line. It's bullshit.
I mean, I see math and physics as kind of like parasitical on each other in the sense that like,
but math describes physics, but you can't use
I mean, math lets you evaluate the consistency of your ideas. It's like, at the end of the day, you gotta, have physical logic. In the sense of, like, we have these physical principles, they relate to our experience, and then the question is this mathematical construction consistent?
Right. But you got to start with empirical evidence and try to explain it using the language of physics, which is math. But because you developed a math theory doesn't mean it applies to the real physical world.
Let's let Matthew start. Let's let Matthew start his presentation.
No,
do we have a presentation?
Yeah, I got a little.
I thought this was just for me to pontificate.
I mean, it just seems to me that, like, it would be nice to be able to work just with a kind of physical logic principles, but like sometimes when you like explore the mathematical constructions, like you get ideas for like new physical principles you haven't thought of, and then it feeds back in the kind of
absolutely. And I'm saying string theory and any mathematical pursuit is worthwhile, if for no other reason than it's for its own sake. But to then say that this equates to some physical reality that we cannot test, this violates, Popper's theorem of falsifiability.
Well, it's like that's the point in string theory and like quantum field theory more generally. Like,
Moshe, you look confused.
We're trying to explore the space of all possible things.
Sound is coming really distorted.
We didn't hear you. We're discussing philosophy. Moshe, when's the next New York meetup? Is it next week?
Moshe?
I don't think Moshe can hear us.
Well, today, we'll talk about, like, in some ways, some interaction between a little mathematical construction or a couple mathematical constructions and some philosophical, physical arguments. And I'll bring up a classic one from, a long time ago, from Leibniz.
Matt, can I ask you something? Are you going to relate this to the Wheeler-DeWitt equation?
Yeah, like we're not going to talk about like quantum gravity as such, but like we're essentially going to talk about like the Wheeler-DeWitt equation demands that like the overall energy of the universe is like zero. We're going to talk about exactly that, what that might mean, why we might think that, what consequences does it have. All right, let's do this thing. So yeah, I got a little, some notes written up here. As usual, if you go on this heyredhat.github.io, you can check out the notebooks. So this one's, clocks. There's a little bit less code like inline in this notebook. At the same time, there's going to be some cool visualizations, which we'll get to. So, okay. Oh, let's admit somebody. Okay, so the question is about time and about clocks. In the normal formulation of quantum mechanics, time enters the equation like a classical variable. If you have some state, psi, you can introduce some time dependence to it, if you know the energy operator. So you just stick a e to the negative I et in front of your psi, and you're good to go. We talked about this, in some of the previous meetings. We went into solving like examples. Oh, I'm getting a little feedback.
Yeah, we're getting weird sound effects.
Maybe it's my fault. Let me turn down my volume a little bit. If that continues, I'll just go to actually, let me get my headphones.
Good idea.
All right, cool. Hello. So if we have some quantum state, any old quantum state, we know the law for energy, then we can introduce some time dependence. So we can know what will happen in the future. But what is this variable t that's popping in there? You know, it's not an operator, it's just a number. And t is apparently the classical time, like measured in your lab. You have like a little clock, you know, on your workbench or whatever. And, you know, compared to that clock, the quantum state evolves in this way. But, you know, time should be quantized like anything else, right? Rumor has it that just as position and momentum are conjugate variables, we'll come back to that, what that means. Energy and time are supposed to be conjugate to each other. And again, we'll come back to this, but you know, if we Fourier transform the position operator, we'll get the momentum operator. So if we Fourier transform the energy operator, we should get a time operator. But it's not clear how that operator relates to this classical time variable that appears here. So the answer ultimately is that we need to consider the clock itself as a quantum system. And it's going to be entangled with the system that we're interested in. And you know, the way this works is a completely natural extension of what we talked about in the last meeting. So like last time we talked about, you know, the idea of sometimes it's called steering. Looked at two qubits and they were entangled, and for every state of the one qubit, projected it into that state and looked at where the other qubit would be steered to due to the entanglement. And so we were able to relate states of A to states of B and visualize entanglement in a cool way. And so this idea of, you know, could call it steering, is also basically going to be the principle that allows us to recover, you know, this little classical time variable out of the entanglement between a quantum clock and a quantum system. So suppose we have a quantum system A, and it's got an energy operator EA. Ultimately, we'd like a quantum clock C to parameterize the time-evolved states of our system A via entanglement. So if we project the clock in all of its clock states and look to see how A is steered due to the entanglement, we want to find A to be in the appropriately time-evolved state, re the Schrodinger equation. Now you can imagine just sort of like mathematically constructing that. You know, you could just, you know, you have all your clock states, like, you know, some orthogonal basis for the clock. You have some initial state for your system. You have a unitary operator, you know, that evolves at this much in time, that much in time, more in time. And you know, tensor up the, you know, each time evolved state with the state in the clock, add them all up, you get this entangled superposition. You can sort of construct it that way, but that's, you know, just, you might say, the mathematical construction. Like, it's not that hard to set up these correspondences between two systems. Question is, you know, how can such a thing actually arise physically? So as a first stab at this, and ultimately we're going to look at 3 different ways to get this effect, all of which are interesting. And the first construction we're going to consider is one due to Feynman, who, you know, is kind of the grandpappy of quantum computers. And he introduced this model in the context of, you know, quantum computation. And the idea is we have a joint system and clock Hamiltonian such that transitions in the clock drive some chosen unitary evolution on the system, leading quite rapidly to the desired entanglement. So suppose I have some qubits and I want to run some quantum circuit. Consists of a series of unitaries, step by step, acting on the qubits. So that could be seen as evolution under a time-dependent energy operator, in the sense that the, you know, the energy operator is different at each tick of the clock. And so you could sort of rephrase the question as, could we describe the same process using a time-independent energy operator? And the answer is yeah, if we include a clock. So, you know, if we label the pointer states of the clock, and like think of these like literally like a clock, and the possible, you know, pointer states of the clock are like literally the clock is showing this hand, you know, this hand, you know, 6 p.m., whatever. So we label the pointer states by T. And, you know, I mean, you can just think of them like, for now, just like integers, you know, T is 0, 1, 2, whatever. And then we have some unitaries in the circuit, ut, one for each t. And then we construct this little Hamiltonian right here. So we sum over all the t's. Now, actually, you kind of want to just sum like to all but the last one, because as you see, each term involves t and t plus 1. And see, if you look at this expression, what is it? It's a sum, okay. For each t, there's 2 terms. And you're taking the unitary at that time, and you're tensoring it to this little transition operator here. So this first transition operator here, you know, if you give it a t state, it's going to give you a t plus 1 state. And this one over here, you give it a t plus 1 state, it's going to give you a t state. So what this does is it couples forward transitions in the clock from time t to t plus 1 to the unitary evolution ut on the quantum system of interest. And it couples backwards transitions in the clock from t plus 1 to t to the reverse unitary evolution, just the, you know, conjugate transpose of the unitary. Now, these unitaries ut, they could all be different from each other. Like, it could be whatever you want, or they could all be the same. You know, so for example, if you just wanted like one, time evolution, you could imagine just sort of discretizing it. You could take just like some one Hamiltonian h, and get a unitary that like evolves under that, just for a little dt, and use a clock with many, many clock states. And then it would basically be, now you've like discretized this evolution for as many states as the clock has. And if you're feeling fancy, you could imagine the clock to have an infinite number of clock states, no need to stay finite dimensional, and then you can regard the clock as basically a free particle on a line. And notice, like, this is not a clock that goes in a circle. We'll talk about that in a second. This is like a clock, it's like a line, right? It's time just goes off to positive infinity. So suppose we have a qubit and a clock. The idea is, like, if we start the clock at t equals 0 and put the qubit in some desired initial state, then turn on this Feynman energy function, the clock's going to begin to tick, synchronize with the evolution of the qubit, and very soon the system is going to reach an entangled state such that projecting the clock into its different time states using a little projector gives the state of the system after the requisite number of unitaries have been applied. So let's see it. Bum, 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 bum. Ooh, cool. Okay, so what are we looking at here? We have, okay, to the left is our spin. And it is, in general, like a mixed state. It's a density matrix. And so, as we well know, its expected spin axis is going to lie, in general, somewhere inside this sphere. Now, just for fun, I've taken the density matrix and I've taken its spectrum. I've looked at its eigenvalues and eigenvectors. And the points on the sphere corresponding to the two eigenvectors are given by this red and this orange point here. And the opacity of them is given by the probability that the spin is in that state. And that's actually just another way of rewriting this spin axis. I just thought it was kind of cool to look at. Meanwhile, on the right, we have the clock. And so you see that the clock has 1, 2, 3, 4, 5, 6, 7 clock states. That was just an arbitrary choice. If you look in the code, you can make that whatever you want. The little red dot here is the expected time. So, the opacity of these little arrows in the clock represents the probability that that's what time it is according to that clock. And the expected, like the average value, is given by that red guy. Now, I chose, a initial state and a 2x2 Hermitian energy operator for that spin at random. And for reference, I evolved it in time just using the Schrodinger equation discretized in 7 steps. And that's what you see surrounding this clock here. So this has nothing to do with what's happening like in terms of like it's moving around, like it's evolving like right now. This stuff like around the edges of the clock, that's for reference. So that's saying like at this time, that's the state it's supposed to be in, just according to the Schrodinger equation, no quantum clock, you're just doing things normally. And so the idea is like the qubit starts in this state, and then it's evolving under its function, and the next moment should be this, and then this, and then this, and then this, and then this, and this. So that's how we're gonna see if our answer is correct, right? So the idea is like if we should project the clock into the different clock states, then this state should be steered to whatever this guy is showing, outside here, like, on the border of the clock. So we could do that. So basically, there's sort of like a janky kind of little program here, but what I can do is, okay, I press R, and this toggles the clock projector. So now you see there's like this bigger arrow here. So that means we're projecting the clock into this first clock state here, leaving everything else the same, and we're seeing where the spin to the left gets steered to via entanglement. And you see that, even though it's like still evolving or whatever, like this state here is exactly the state that the spin is steered to. If I, oh shit, sorry. What's the key? Oh yeah, T. Okay, so now I can, look at all the different projections. Suppose the clock was showing this time, or this time, or this time, or this time, or this time. I can see where the spin is steered to. And you can see that, indeed, the spin is steered to entanglement in exactly the right state given by the normal Schrodinger evolution of the spin as an isolated system.
Can I ask you a question?
Yeah.
Entanglement, correct me if I'm wrong, entanglement is independent of space or time. So how can we discuss entanglement with a time operator?
Well, when you say independent of space and time, I mean, it's not really.
Doesn't matter how far you separate two entangled particles in space or in time.
Yeah, so I mean, so what you're seeing here is there's a clock and a spin, and they're coupled together. So I mean, there's like a joint evolution given by that Feynman Hamiltonian that is making them interact. So I mean, the entanglement is not fixed in time at all. I mean, it's changing as this thing is evolving.
But it seems that the entanglement depends on the clock.
How do you mean?
Well, as you rotate particle A, it takes a finite amount of time for particle B to rotate.
No, it's like it's saying that like, so okay, I'll do this thing. So instead of like projecting, like doing that little projection thing, like let's like measure the clock, right? So what I'm going to do now, if I press the C, what it's going to do is it's going to like look at the probabilities for each of the clock states, and it's going to project it into that clock state with the requisite probability. Boom.
And this occurs instantaneously.
So yeah, so well, I mean, it's like you like are outside the system, you're the experimenter, and now you're like going in, you're like measuring that clock. And boom, you see that like when you project it, the spin, gets pushed to exactly the right state that it should be like at that time. I'll keep doing it. Ping.
I don't see where time gets in. It comes into this. Space obviously doesn't. You can separate the particles as far as you want.
It's saying that instead, okay, when you encode this relationship with entanglement, you're encoding the time evolution of the system timelessly in the entanglement between the clock and the system. So I'm going to come back to that point in a second when we see the next example, which will make that even more clear. So, if
May I ask, is the clock something that could, in principle, be a system in isolation, and you can just, just for simplicity and reference, think of it?
Not in this case.
No. Okay.
This is not an isolated clock. We're
So
going to have an example.
There's no meaning to it unless it's tensor product into.
Yeah. So this is a clock which is actually driving the evolution of the system. It's not independent. It's interacting.
Is there maybe an intuition, a physical intuition to realize that as a situation we can think about? Like, how would a clock drive a system?
So, it's like, right. So Feynman introduced it in the sense of like, okay, so we build a quantum computer. We want maybe some flexibility in like interacting with it. You know what I mean? So we could like, actually, I'm going to come back to that point when we talk about the next model. If you'll forgive me for that. So wait.
But Matt, entanglement does not evolve, and I don't believe you could say it's unitary in the sense that it evolves.
I mean, what do you mean? It's like, you can see quite clearly from the code that, there's a unitary operator and you're watching it like evolve these things in real time. And in addition to seeing it evolve, there's this, the particular entanglement between the spin and the clock gives you the same result, as I say, as if you just took the normal Hamiltonian of just the spin and evolved it discretely in time. So like, for example, let's measure the total energy of the clock and the spin together. That leads to a time-independent state. So a state of definite total energy does not evolve in time. And so you see that the clock and the system both are frozen. And in fact, in this state, the requisite entanglement is not there. You can see, in fact, that if I project the clock into all the states, the spin doesn't care. If instead I just, so, again, like start it over. Let's start the spin and the clock in their initial state. Ping, you see it starts and it's just the clock's, turning. Oh wait, let me turn the projecting off. The clock's turning, and meanwhile it's driving the right motion of the spin, and then it kind of like, backtracks and stuff like that. But almost immediately. So, okay, I'll turn off the time evolution. So I've paused it. Now I start it in the initial state. So now the clock's in the first moment and the spin is in the first moment. And I'll turn on the projection and I'll look. Like in that first moment, the entanglement's not there. Nothing's happened yet. There's no entanglement, no steering. But you'll see almost immediately, if I let it evolve for just a second, like ping, that entanglement is now there. The two things have become entangled. And now the states of the clock parameterize the time evolved states of the spin. Now, metaphysically, we'll come back to this issue about entanglement being independent of space and time. Because like, you're not wrong, but this, that's going to be much more relevant in the two constructions we're going to see next. So, there's a couple other things before we move on from this that like you can do. You can see like, oh, what if we just, pop a random state in there? I have ways where you can kind of like, rotate this, qubit to see what happens. I can, shift the clock around. Like there's an operator that does that. You can play around with this, does different things. So any questions about that before we move on? The questions you guys have asked have been totally on point. I think some of them will be answered in what follows.
Is there a sort of symmetry that it seems like there are, since the clock states can sort of range negative infinity to infinity or something, and the spin states are sort of constrained to some range, that you can parameterize the evolution of the spin state by the clock and not vice versa. But just looking at the Hamiltonian, I mean, is there some significance to looking at, like, the spin is also sort of, I mean, other than the time having this nice parameterization feature, is there any reason to emphasize it as the sort of dominant component of the system? Because it looks like you just have transitions in time are coupled to evolutions of the spin.
Yeah. So, you can choose arbitrarily, like, the dimensionality of the clock. So, like, if you look at the code, I just chose 7. So it's not like you could have the clock be like a particle on a line where, like, literally it's like an unbounded clock, like, time can just go infinitely far into the future or whatever. In this case, I mean, I just chose it to be a finite dimensional clock. So if you look at the code, it's a choice. You can plug it in right here. I can just choose, I just chose 7.
So if you were to choose, let's say 2, then would this become kind of like 2 spins entangled?
I mean, like, no, so like the clock and the spin would be both 2-dimensional, but I mean, I guess like the physical interpretation of it would be different.
I mean, well, two state systems entangled.
Yeah, so like, I mean, in the spin case, the relevant thing is that, the basis is like given by eigenstates of like the Z operator or whatever. Like, for the clock, it's,
it sounds like it doesn't have its own independent Hamiltonian. Like the clock states are not eigenstates of some defined Hamiltonian.
In this case, they don't have separate Hamiltonians. There's just this one Hamiltonian that like couples the two of them. We're going to see an example where they do have separate Hamiltonians. That's going to come up. That'll be the third thing that we talk about.
Matt, question.
Mm-hmm.
I could see this is non-relativistic so far, but in what reference frame, in general, let's say you extend this to QFT, in what reference frame is the clock?
Sure. Yeah, I mean,
are we just talking about a non-relativistic situation?
Yeah. Basically. Like later on, I mean, I give a sort of a toy example. I wasn't necessarily going to go into it, but of just like a 1 + 1 dimensional, like Dirac equation type thing. And there's some interesting subtleties there.
I mean, let's say the particles are moving away from each other with a significant velocity. In what reference frame or even accelerating away from each other, in what reference frame is the clock?
Well, I mean, I'll say something that might be a little sloppy, but I mean, arguably, your choice of clock is your reference frame.
But if you have 2 particles that are not in, the same reference frame.
Well, that would mean that there's 2 clocks.
Which particle does the clock apply to?
Right.
Or does it apply to both?
So in this case, because
if they're not inertial reference frames, what I meant.
Yeah. So in this case, I mean, you could, this is one where, as I say, the clock drives the evolution of the system, and so there's an interaction, and so, in that sense.
So the clock is in whatever reference frame you want it to be in, relative to a particular particle.
Yeah, whatever you want to say. It's like it's in this case, like regard it as being in the same reference frame as the spin that it is clocking.
No, but the spin is independent of reference frame, really. Like I said, if you have 2 particles in non-inertial reference frames, or even in inertial reference frames, which frame does the clock apply to, or does it apply to all reference frames?
Yeah, but like, what is a reference frame? It's a choice of a clock and a ruler and other things. So, I mean,
right.
I think it's sort of like, in a way, you've answered your own question. I mean, this is, you could argue like, this is what a reference frame is.
So it applies to both.
Like,
it applies to both particles. The clock applies to both particles, even if they're in non-inertial reference frames. But of course, relative to each other, the clock would be ticking at different rates.
Yeah, well, yes. Well, I'll come back to this issue.
Is the, sorry, is the t in the clock state, is that literally the same t in the time derivative in the Schrodinger equation?
Yes.
Or is it meant to be sort of an artificial proxy?
So look, so here's the code. So, you know, this is the thing that, for example, generates that circle of states around the clock. So I choose a random initial state for the spin. I choose a random energy function for the spin. Then I choose my dt, my little dt, to be 2 pi over the number of clock states. So it's 2 pi over 7 in this case. And then I create a little unitary that evolves, you know, that's based on this, this randomly chosen Hamiltonian, and it evolves at just that little dt. And then I can introduce time dependence to my initial spin state by just being like, okay, here's a function of t, and I just stick that in here. And then I develop this history. This is just like an array, and it just goes through the, you know, all the, you know, 1 through 0 through, you know, 6, I guess, because there's 7 of them. And it evolves it with the Schrodinger equation, you know, by that time step. So that's just the normal Schrodinger evolution. Okay. And you can see that it's exactly the same as if we, you know, here we construct the Feynman Hamiltonian. Here's like the projectors that project the clock into all of its time states, and so forth.
But again, Schrodinger's equation assumes the same reference frame for all the particles. You know, they're not moving; they're stationary with respect to each other.
Yeah, I mean, in this case, there's just 2 things. It's just a clock and a spin. So I mean,
and it's also the Schrodinger equation doesn't treat time like a state or some observable. It's a parameter. But
exactly.
I guess that's my that's the subtlety that I'm, because it just seems to be serving as a label, like a state, you know, and a parameter.
Yeah, and so arguably what we've done is we've upgraded it from a classical variable to instead be the eigenvalue of the time operator of the clock.
You mentioned the possibility of a wave function for the universe, and so by not restricting to a reference frame in this instance, is that what you're leading towards?
Yeah, we're about to come to that, totally.
Okay.
That's Wheeler-DeWitt equation.
Yeah. So here's a stepping stone in that direction. Okay. So Kitaev, another great physicist with lots of great stuff named after him, has a similar construction to the Feynman one. And so before the Feynman one, it was like the clock in real time was like driving the evolution of the spin, and it was entangling them. And so you could see, you know, in the animation, you know what I mean? It's like the clock's turning, the spin's rotating, you know, in synchrony or whatever, and then it kind of like gets a little fuzzy or whatever, and you get your entanglement. So what we're going to do now is generalize it to encode that exact same entanglement between the clock and the spin in the timeless ground state of a Hamiltonian. And this is it. So here's the Kitaev clock. So it's a sum over the time states again. The first 2 terms are just the same as the Feynman clock, except now they have a negative sign in front of them. And they're counterbalanced by these 2 terms here that just act on the clock. And then finally this term here, which you can think of as imposing the boundary condition. So this like imposes this relationship in a sense. It's like setting it, what is the, you know, when the clock shows 0, the spin has got to be in this initial state. This energy operator will have a 0 energy eigenstate, hopefully, which corresponds to the entangled state that we want, the same one from before. And this entangled state encodes the entire history of the evolution of the system relative to the clock, all at once, simultaneously, in the spatial entanglement between the clock and the system. So it's like, you can think about it like, instead of like, you know, you can do one of two things. You could like watch a system evolve in time, or you could encode exactly that same thing timelessly in the spatial entanglement between a clock and a system.
Well, that's a block universe.
Well, yeah, in a way.
In a blockchain.
The blockchain universe, yeah, right.
Not a blockchain, but a block, which we may be living in. Time may be an illusion.
So what I'm going to say is that, you know, it's like a block universe in the Einsteinian sense, except, and I'm going to come to this point, you know, at the end, you get, say, you know, these things, although they might be timeless, they only let you predict outcomes up to probabilities. And so even if it's an eternal block universe, there's still free choices. Things are not determined from the beginning of time. Things are just defined probabilistically.
Remind me what a block universe means. What is it?
Block universe is like, picture a bread loaf, and that's the history of the universe. You know, each slice of the loaf is a moment in time. And, you know, Einstein says, well, you can slice the loaf however you like, and you get, you know, different evolutions of this eternally existing thing, you know, which is like all of history is.
But the important thing is that all of the past, present, and future is already here, and time.
Like Slaughterhouse 5.
Time is
totally.
Our illusion of things going from one to another.
Okay, whereas a non-block universe is something where it's much messier than that. You can't.
Well, no.
What does it mean to be a not a block universe?
Time. The time is real.
Yeah, right. Yeah, I mean, you can. I mean, there's many things you can imagine that are like not block universes. I mean, one where, you know, in some sense, the future is generated in a novel way from the past that can't be predicted beforehand, you might say.
Okay.
Well, that's Taylor's theorem, but I don't think. But quantum physics, you know, dispels that. But the point is, the block universe just says that time is our illusion of what's going on. That everything that ever happened or ever will happen is fixed in stone, so to speak. And we go from one point to another. It's just our illusion of time passing.
Yeah, we're going to come to this exact issue momentarily, I promise. Okay, so we got this Kitaev clock. Now, so I wanted to mention this. So far, we've just, you know, I represented the clock in the previous instance as like a clock, you know, like a circular clock, but, you know, it wasn't really circular. Now, you can do a circular clock. So we can update this Kitaev Hamiltonian, for example. And we just have to add terms that couple, like, you know, the 0th time state, you know, to the last time state and so forth to make the clock circular. But there's an interesting restriction, which is that all of the unitaries that you use have to all multiply to the identity. So you can use a circular clock only if the computation is sort of done and then like undone in the course of the computation. That's sort of like a sidebar. It's kind of interesting. And it kind of relates to me, that might remind you of something like a gauge theory, because you're thinking about like a loop or something. Now, of course, yeah. So, which is to say, in principle, I mean, your clock like could be kind of anything, right? Like a clock could be states on a line, states on a circle. Why not states on a network where, you know, unitaries parameterize shifts between nodes in the graph? And then, you know, you start to get something that looks kind of like, you know, like a gauge theory. That's just an aside. But okay, so what is like the particularly cool part about this Kitaev Hamiltonian? And this, you know, gets at the issue of like, you know, realizing it in the lab and like why it would be even useful to do this. So it can be used for a really powerful way of doing adiabatic quantum computation. So the idea is, you know, suppose you got your apparatus and there's some dials on it, okay? And you can choose, you can tune what Hamiltonian you want by adjusting these dials, okay? So like you start off with your quantum system being in a really simple Hamiltonian, like a not complicated one. And you start cooling the system down. Like, you know, you're letting it interact with some stuff, like cool, like lowering the temperature. You want to like cool it down to its lowest energy eigenstate. This requires some effort. And it's easier to cool it the simpler the system is. So you've like try to cool the simple system down to the 0 energy eigenstate. And then very slowly, this is the important part, ever so slowly, you turn the dials and transition the energy operator from the simple one to the Kitaev Hamiltonian. And the idea is if you do this slowly enough, then at the end, the system will still be in the lowest energy state, but now the 0 energy state of the Kitaev energy operator instead of the one that you started out with. Then you can access any moment of your computation by just measuring the clock. All the difficulty of actually running the computation is traded for the difficulty of cooling the initial system and ascertaining through measurement that the Kitaev computer is actually in the 0 energy state, after which it's guaranteed to stay there if there's no interactions, because I mean, it's just sitting there in this ground state, not evolving. The whole history of the computation is encoded timelessly in the ground state of the system. And from there, you can read out which answers you're interested in via measurement. And what's particularly nice about it is you can recover from errors by just cooling the system back down to 0. It kind of like resets everything. So I have a similar visualization. Kitaev clock. Okay, well, so here it is. I mean, shock. Looks exactly the same as before. It just doesn't change in time. So, you know, if we look at the code, we do the same thing as before, but now we have our Kitaev Hamiltonian. And we just go through and look at the 0 energy eigenstates, you know, of this Hamiltonian. If there's more than one, we just add them up. Doesn't matter. Come back to that point later, but you know, we just take that to be, that's just the ground state. And that's where we start. Here it is. Doesn't change in time. But you see, if we do our projection from before, blammo. We project each of the clock states, the clock in each of the clock states, and we have the entanglement that we want.
You are talking in part about all of this in relation to what I'm referring to as the subtext, which is quantum computing. So given that we do not know the exact nature of entanglement, we simply observe it or observe it to a degree. And since entanglement can occur itself in different degrees within, in the relationship between two quantum systems. Mm-hmm. What about the possibility that occasionally the entanglement is purely accidental and that it disentangles more quickly than a genuine entanglement, and now you're basing your quantum computing system on entanglement and it is not reliable? What happens with your computations?
Yeah, totally. So, I mean, with this, you gotta build the system, you know what I mean? You gotta like construct, clock system, get this Hamiltonian that couples them together and then cool it down to its ground state. So yeah, I mean, it's relative to your ability to do that. Now, the thing we're about to talk about kind of changes the game, and it gets at like all these concerns that you guys have been bringing up, because in some sense we've been doing something that's not really like a clock like that we normally think of it, right? Normally the clock does not interact with the system that it clocks, right? Normally the whole point of it is that it's separate from everything else. It's like doesn't interact, like your wristwatch or whatever. Like the point of it is that it's like ticking away like imperviously to whatever is going on around it. And so you might wonder, like, what if we have our normal notion of clock that's separate, has a completely separate energy function from the system? Is there a natural way that this kind of entanglement can arise in that case?
I almost wondered if the reason that you were even talking about quantum clocks is because of the precision. I think I just read that they already have a quantum clock that doesn't vary more than 1 second every 32
yes.
billion years. And so the purpose of even discussing this was to try to have a quantum clock to look at the issue of entanglement and look at the issue of, you know, so-called simultaneity in the entanglement, which is, you know, seen as an impossibility by many, and whether you were that's the reason for your whole discussion of the quantum clock.
I mean, in some ways, I mean, to be honest, yeah, like we could have discussed, yeah, like the challenge of building a quantum clock in that sense. Like you want whatever, a cesium atom or something that's just like, you know, very reliable little oscillation or something like that, which would be important, like in all these cases where you're building like a, you know, some kind of quantum system and you're trying to coordinate things, and, you know, the accuracy of that, you know, the time scales at which you're going to work.
Well, Matt, John Bell proved that no matter how accurate a clock you have to measure entanglement, there are no hidden variables, as Einstein believed.
Yeah, totally.
It doesn't matter how accurate your clock is. Entanglement doesn't involve that. Doesn't involve time.
You know, you know, in a way.
There are nothing but hidden variables, not in the original sense of hidden variables, but there are nothing but hidden variables on the cosmological level and on the quantum level, with, you know, weakly interacting massive particles and particle-antiparticle pairs coming into existence. And we don't have a sufficient understanding of the cosmos at a cosmological level to know exactly how each quantum system is being affected locally, regionally, and cosmologically.
No, but Victor, it doesn't matter if you're talking about atomic or cosmological. John Bell proved that when it comes to entanglement, there are no hidden variables.
I don't buy it. That's a specific definition of a hidden variable, but I don't buy it.
Right.
It's been proven and tested empirically.
It is specifically
the assumption of that.
It's limited to the particles themselves. So it is not. So it doesn't take into account that, for instance, right at this second, I have billions, every square centimeter or cubic centimeter of my body has billions of neutrinos passing through it. And while there's virtually no interaction between the neutrinos and the particles in my body, there are occasional interactions. And we do not know the exact nature of the particle.
But those are not faster than light interactions.
I'm sorry?
Those are not faster than light interactions. Those are local interactions. And like I said, John Bell proved that entanglement is not local. Unlike all the other interactions you're talking about, entanglement is very special. And yeah, Einstein made the same argument you're making. But again, John Bell, I think in 1965,
I know
mathematically, entanglement is not local.
He's in error because
he's in error. Okay.
Nature does not play dice.
Okay.
Oh no, this has nothing to do with dice. That's a whole other thing. That has to do with measurements.
If we knew every parameter that was actually affecting the quantum system, then even with our affecting the nature of the particles through our observation, or the qualities of the particles through our observation, if we knew what all the parameters were, there would be less uncertainty.
No, but you're talking about locality, which again, Einstein believed in, but he was wrong. You're talking about locality, and most of the interactions in the universe are local, involve locality.
Figure this out.
Entanglement is a whole different thing that does not involve locality.
Well,
the challenge to a very fundamental point of quantum mechanics that, you know, is not the time, I guess, maybe to try to resolve it now.
Yeah. Okay.
I mean,
well,
no,
it was
You have to
resolved.
revisit all kinds of assumptions that
It
you've
was
made to
resolved
get to this
45
point. You know?
years ago, so we don't
well,
have.
look, I mean,
Yeah,
I think
I buy it.
everyone's kind of right here in a sense. I mean, the assumption in Bell's theorem is that, interactions are local or something, right? And that the hidden variables are local. So, I mean, you can kind of like come up with a picture of quantum mechanics where there are like non-local hidden variables that can kind of like reproduce a lot of quantum mechanics. But
The other thing
kind of like,
I think is just so convincing for me is that Cohn-Specker theorem and the example of the situations in which it's impossible to for a system to have every kind of feature you would want it to have if like realism were fully fleshed out. Systems that don't, it's not possible to have a consistent label for all of its momenta that you could in principle measure. That seems to be more convincing than just the Bell's theorem, which is I'm convinced by. But.
Sure. Well, so I think that what we're about to talk about will like kind of contextualize all this in a nice way that you guys will appreciate. Because now we're like going to talk about, like in a sense, the cosmological thing. It's like, this is like the Wheeler-DeWitt part, okay? And it's going to like, it'll be good, okay. So we're going to take our inspiration from this Kitaev clock, where we encoded the entire history of a system relative to a clock, and this whole thing is in a zero energy eigenstate. We can take a temporal sequence of a individual quantum system and express it all at once, timelessly, in terms of spatial entanglement between a system and a clock. And this kind of thing has been done in the lab. There's a cool paper you can look at here. But now let's like get at like the essence of kind of the philosophical concerns that we have. So I want to go back to a famous series of thought experiments from the early modern European period. Leibniz, the philosopher, famously was getting into all these arguments with Newton and the Newtonians about the nature of space and time. And Newton, well, who knows what Newton believed, but Newton is associated with the notion of an absolute space-time. Space and time are the sensorium of God, and matter is God's ideas. In any case, Leibniz was like, I think space and time are relational. They're not prior, but in some sense emerge out of the relationships between things in the universe. And his thought experiments went like this, who could tell if someone moved everything in the universe 3 feet to the left? Nobody. No one in the universe could tell, since everything would have been moved equally as everything else. Therefore, although things in the universe have distances relative to each other, the universe as a whole ain't nowhere. There's nothing outside the universe such that a difference of 3 feet to the left could be noticed. So it's inappropriate to say that the universe as a whole has a location. It is placeless. The notion of place is a concept that relates things within the universe to each other. Similarly, who could tell if someone pushed all the clocks forward 5 minutes? There's no clock outside the universe by which this change could be registered. So things inside the universe change relative to each other, but the universe as a whole has no time. It is timeless, or perhaps better yet, time independent. So now we know in quantum mechanics, time evolution is given by the Schrodinger equation, as we well know. So we're saying something like the state of the whole universe has to be time independent, just from this kind of relational, relativistic, Leibnizian kind of argument. And so we can ask, like, well, what are the timeless states in quantum mechanics? Well, they're just the energy eigenstates. A state of definite energy is timeless, except for a phase evolution given by the eigenvalue of that eigenstate. It's only superpositions of energy states that evolve in time. And indeed, if the particular energy state that you're using has eigenvalue 0, then it doesn't even have a phase evolution at all. The state will be completely invariant, just in the sense that, if they take like e to the eigenvalue, and the eigenvalue 0, that's just, 1. So if we believe Leibniz and we want to make a quantum model of the entire universe, we should demand that the whole universe be completely time independent. So we're assuming that there is some law of the universe that gives its total energy. And that operator, when it acts on the wave function of the universe, psi equals 0. This psi is taken to be the global state of the entire universe, and it contains the very clocks with reference to which things evolve in time relative to each other in the universe. Okay. So like before, when we were considering the Feynman and Kitaev constructions, which instigate interactions between the clock and the system, sorry, that was a weird sentence. Yes, so we were considering interacting clocks and systems before. But let's do something almost even insanely simpler. What if we actually demand just the opposite? That the clock and the system have nothing to do with each other, that they are completely separate, commuting, independent operators. And indeed, this is like our traditional conception of a clock, which is just tick away imperviously to what goes on around it. Now, here's the theorem. Here's the cool part. It turns out, if we have two systems, like a clock and a spin, say, with separate and commuting energy operators, such that the total energy is the energy of the clock plus the energy of the spin, and if on these relativistic grounds, we demand that, in a sense, we demand the Wheeler-DeWitt equation, E times psi equals 0, then psi will be a maximally entangled state between the two systems, with the property that projections onto the eigenstates of something, a time operator of the clock, project the spin B into exactly the states predicted by the normal Schrodinger evolution of B at the classical time t, now interpreted as the eigenvalue of the other system's time operator. What's the time operator? We're going to go into this. It's the Fourier transform of the system's energy operator. And what this theorem is saying is that independent subsystems constrained to exist in a time-independent universe together automatically parameterize each other's time evolution. And this is known as the page orders mechanism. And
Matt,
the original papers are from the early 80s.
But Matt, doesn't this only apply to a non-relativistic universe? Once you get
this applies to all universes.
So then is this the block? This sounds like the block universe to me.
Yeah, but again, it's a time independent picture of the universe. Yes, all of history contained in one state where the relationship that we normally think of as temporal is represented as the entanglement between the different clocks in the universe and other things in the universe. Each system in the universe acts as a clock for the rest.
But question,
Mm-hmm.
does this only apply to the entire universe, or can it apply to subsystems?
So the argument, is kind of, I mean, if you follow Leibniz's argument, it's like an argument about the universe as a whole. And at the very end, I'll bring up, we should talk about it then, this question of like how, philosophically, necessary it is. I mean, one could argue, fuck that. I mean, I think that it's insane that humans could contemplate the state of the entire universe as maybe an incoherent concept or something, but let's assume that that's possible for the sake of
I had a similar question, maybe it's already conveyed in the previous one, which is if the whole universe is in an eigen, and there's a wave function for the whole universe, and I'm in it, and I'm doing quantum measurements, and I'm causing local wave function collapses, what's happening to the universal wave function as local things collapse?
Yeah, great question. Totally. I'm going to come to the answer. Yeah, that's coming up.
And again, just another question. Isn't this just the restatement of conservation of energy?
Yeah, I mean, it is it's sure. I mean, in a way. All right, so we have two systems, A and B. They each have their own energy operator, EA and EB. And they commute. So, I mean, one way you can get that is like if there's a tensor product structure. In life, there isn't always a tensor product structure. In finite dimensions, there is. In infinite dimensions, it's not always the case. But let's assume there is just for now. Doesn't really affect the argument all that much as far as we're using it. And so we could write, the total energy operator would be like, EA tensor the identity on B plus the identity on A tensor energy of B. And this will guarantee that the two operators commute. Okay, here's just a sort of sidebar observation. So we want to demand that the overall energy of the universe is 0, but like depending on the, energy operators of the systems in the universe or whatever, there might not be any 0 energy eigenstates. You might have to rescale some eigenvalues or whatever. It's like, it's not. And so you could say like, if there aren't any 0 energy eigenstates, then these things can't coexist in the same universe. Furthermore, maybe there's more than one 0 energy eigenvalue, in which case there's these degeneracies. And so, the 0 energy subspace is, multi-dimensional. It's given by, linear combinations of all of the different 0 energy eigenstates.
I'm used to thinking of energy as always being only defined up to some constant, additive constant.
Yeah.
So is it really necessary that it's numerically equal to 0, or that there just exists some ground state that you can sort of decide, like some lowest energy that you can just define in your own
So
way.
like you could rescale, but that's what I was saying. Yeah, you could sort of rescale the eigenvalues, like one of them is 0 or something.
Okay.
Like the important part there is basically like you're trying to model it in such a way that the energy eigenvalues of the different systems are going to kind of fit into each other in a certain way.
Right. So you could equally just say that the energy is a constant, and you can make that constant 0 if that's conceptually pleasant.
Like if you just had like any old, if you can additively rescale the eigenvalues, like the lowest eigenvalue is 1, you could just make it 0 or whatever.
Right.
Okay, so we know that conserved quantities of a quantum system are represented by, operators that commute with the energy operator. And so that says that, in our case, operators that commute with our global energy operator are timelessly conserved quantities. Those are going to be quantities that are conserved for like all time, whatever, time independently. They're like really real, We can consider, so suppose we have this case where there's like degenerate 0 energy eigenstates. So we could consider some like random operator G that commutes with the total energy operator. This, when we evolve the system under that operator, it's going to keep us within the 0 energy eigenspace. And it's going to have no effect whatsoever on any of the globally conserved quantities. It just has an effect in terms of the description of relative quantities like between the systems. And these transformations are called gauge transformations. So if you're ever wondering what those really are.
Well, I have a question. Energy and time do not commute.
Not at all.
So how can we say that time is static or 0?
So, we're saying that, totally. So we're not going to consider the time operator of the whole universe. We're going to consider the time operators of parts of the universe. So, and this is actually great. I'm glad you brought that up because this sort of what we're about to get into. So we're going to go on a little digression about conjugate variables, right? So the classic example of conjugate variables are position momentum, P and Q, and their commutator, P, times Q minus Q times P is I. Famous thing, Heisenberg, etc. And, the idea is localization in position leads to a spread in momentum. Localization momentum leads to a spread in position. The relationship between position momentum is given by Fourier transform. If I have a quantum state expressed in the position basis and I take the Fourier transform of that state, I get the state expressed in the momentum basis. And I can also do the same thing to operators. If I Fourier transform the position operator, I get the momentum operator. Now, in case people don't have a gut feeling for Fourier transforms, I just thought I have a cool little thing. So this is not quantum at all, but this is fun. So this is, oh, can I not do this? Oh, rats. I might have to turn off my microphone to do this because okay, so what I, just for like fun, I put together like a little frequency analyzer. So it listens to the microphone and it displays the waveform of the sound that I'm making. And then it takes the Fourier transform of the last couple milliseconds of that. And then you can see the spikes at the different frequencies in the tone that I will make. Now, unfortunately, it seems because Zoom is using my microphone, this doesn't work. I didn't think of that. Let me turn off the Zoom, my Zoom. How do I freaking do that? Okay, mute. Alas, I don't think it's going to work. I'm sorry, I didn't
Are you
anticipate
using like
that.
a Python library that connects to the computer's
Yeah,
inputs?
that I am. There's a nice Python library called PyAudio. Well, I mean, I'll upload it to the server. You guys can play around with it if you want. Yeah, you get like, ooh, like you sing a note and you see the spikes, you know, the different frequencies, different overtones in your voice and stuff.
Matt, it's very simple to explain. The Fourier transform is just the frequency components of the time wave.
Yeah, totally.
Yeah.
It's entertaining to watch it live, you know what I'm saying? Okay, cool. So here's the deal. The position operator is the generator of translations in momentum. The momentum operator is the generator of translations in position. And that's like the entire idea. That's like the entire point of conjugate operators. They generate translations in each other's eigenspaces. Now, in the case of position momentum, to get that famous commutation relation, P and Q have to be infinite dimensional operators. And the Fourier transform is given by an integral. And this commutation relation cannot be satisfied by any finite dimensional matrix. So let's, not use that. So let's just work in finite dimensions, okay? Just to make it more concrete. So if you're working in finite dimensions, you can just think of the Fourier transform as a matrix multiplication. And here it is as an n by n matrix. You can see what it does, It's like, you got 1, 2, 3, 4, 5. You got multiples of 2, multiples of 3, whatever. In the two-dimensional case, it's just the Hadamard matrix. Now, to make this concrete, let's just think about spin again. Now we know we have our X, Y, Z Pauli operators that generate rotations around the X, Y, and Z directions. And they don't commute in a way that mirrors the non-commutation of 3D rotations. If you do this rotation and then that rotation, in general, it's different if you do the second rotation than the first rotation. That's just true about normal, classical 3D rotations. And one way of thinking about that is this, that the X operator and the Z operator are Fourier transforms of each other. So like if you, transform the Z operator by the Hadamard operator, you get the X operator. If you transform the X operator by Hadamard, you get the Z operator. And, this is actually intuitive. Okay, I have like an apple here. I can rotate around the Z axis, and what does it do? It generates cyclical translations in the X eigenspace. Like if I start at the point here, like where the byte is at 1, 0, 0, this is like the X direction, I could rotate around the Z axis to get negative 0, 0, right? And then I can rotate around the Z axis again to bring me back where I started. And similarly, I can rotate around the X axis to generate cyclical shifts in the Z eigenstate.
Matt, are you saying that the Hadamard operator performs a Fourier transform?
That's exactly what I'm saying.
But it also is a phase rotation. Isn't that what a Hadamard does? Doesn't it give you a phase rotation? Or maybe
It does. I guess it does more than that. Yeah, it's the two-dimensional discrete Fourier transform.
oh, so it's only two-dimensional. Are
Yeah,
there higher
it's just a straight up.
dimensional Hadamard?
Yeah. It's just the discrete Fourier transform is the higher dimensional Hadamard gate or whatever. Like, so, this is what this W here, for any dimension, you choose the N, and it's like the simplest case is just, oh, I forgot to say what W was. I'm sorry. W is a root of unity that you've divided by N.
Why is it?
I'll put that in.
Why not just call it H?
Oh, why did I call it W? I don't remember.
Oh, it's just to be different from it. It doesn't stand for anything, does it?
No, yeah, sorry. W is just a complex number. That's a root of unity. That's, it's like e to the I 2 pi over n or something, I think. And then you take these powers of it. I apologize.
So could you extend this to a continuous Fourier transform?
Yeah. So like you can think about like in the limit as this matrix goes to infinity, it's just the normal integral that gives you the Fourier transform. Cool. So now this is general. Like we have any given operator and like we could just Fourier transform it to get a conjugate operator and they will generate shifts in each other's eigenspaces. So what happens if we take the Fourier transform of the energy operator? Time and energy are supposed to be complementary. I mean, it's not a proof, but I mean, we're just going to say it. We're going to conjecture that if you take the Fourier transform of the energy operator, you're going to get something like the time operator. And just from what we've just said, what it suggests is that a state of definite energy, like a spike in energy, is a superposition over all time states. And a state of definite time is a superposition over all energy states. Now, if we're just considering a single system in isolation, like this isn't that useful. We have like the Schrodinger equation, as we keep talking about. We can parameterize the time evolution as e to the negative IET, where t is classical clock variable. This is repeating what we've said before. An energy eigenstate is going to be unchanging with respect to that external t. But now we can also say that to be in a time eigenstate is to be maximally changing with respect to the external t. Both perspectives provide a complete basis for the system. In other words, you can expand the state in terms of the eigenstates of the energy operator or the time operator, whatever. Okay, so now we have a universe consisting of two spins, say, A and B. And their energy operators commute. And then we demand that the overall energy of the universe is 0. And what it means is that the energies of the two systems have to be constrained in such a way that like positives and negatives always cancel out to 0. And it's like the wave function is encoding like all the ways that can happen. The system will be correlated via entanglement so that like whatever the energy of A is, B has just got to give the opposite. So that's in terms of energy, but what effect does this have if instead we measure the time operator of the one system instead of the energy operator? So now let's consider our two time operators, TA and TB. We just take the Fourier transform of the individual energy operators of A and B, and we get these time operators. And then let's consider projectors onto A's time eigenstates. They're each going to be labeled by some eigenvalue, and let's call it T. We'll project the global state with each of A's time projectors and see where B is steered to due to the entanglement. This is now something we're familiar with. For each T of A, we have a state of B. And it turns out that relative to this T, B looks like it is evolving under its energy operator EB as if T were the external time variable in the local picture of Schrodinger, evolution, no clocks, etc. Clock is treated classically. And the same goes for B. If we project onto B's time states in turn, A appears to be evolving according to EA. Because of the 0 energy constraint and the fact that they are non-interacting, again, that's important. A and B are going to be entangled in such a way that their entanglement encodes the time evolution of the other. They act as clocks for each other. In the case of two spins, like spin half particles, I mean, this is a very simple clock. Discrete clock can only point in two directions, but, same deal. So
may I ask about, so it's implied that one state is going to have positive energy and the other state's going to have negative energy. And as far as interpreting negative energy, those are usually like, bound states or positive or free states. So is it too soon to try to have a realistic picture of this?
Yeah, I don't want to get too much into that quandary. I don't have anything super smart to say about that. But I will say this, that, you can have, this works for you can have multiple systems, each with their own energy function. And for each independent subsystem, that subsystem will act as a clock for the entire, rest of the universe. Each independent subsystem can be regarded as a clock for the rest.
I guess another motivation for that is, as far as zero energy all the time, should that be like whenever one goes positive, there's something compensating for it, or that everything that ever happens is one or another degenerate state, that all things that you can observe correspond to zero energy? It's all degenerate, and you can move from one to the other. And,
yeah, it's kind of more like
positive and nothing's negative.
I would say it's kind of more like that. Yeah, the second one.
Okay.
Okay. So this is cool. So out of this timeless global picture, we are able to recover time as a relationship between parts. Now modeling clocks themselves with quantum mechanics. The clock could be a spin, a free particle, anything. What's important is the conjugate relationship between time and energy and the global entanglement. And here's an observation, each independent subsystem is entangled so that its time states parameterize the Schrodinger evolution of the rest of the universe according to the rest's own energy operator. But what determines the initial state, or whatever, relative to some clock at time 0? Well, the initial state's going to depend on, the symmetries of all the different subsystems. And so it's kind of an interesting philosophical point that the question of what's the initial state of the universe is replaced by just what is the time independent state, for everybody. And then the initial state observed by each observer is entirely determined by what systems it shares the universe with. In other words, the initial state for each observer is determined entirely by the relations between the things in the universe. And it really is quite like, and you got to figure, the people come up with this stuff, they've all read Leibniz. It really brings to mind Leibniz's famous picture of the monads. I don't know if you've ever read the monadology from, the 1700s, but the idea is like the world, according to Leibniz, is made of monads, each separate from each other, each in their own place, but each in their own way reflect the whole, so that despite being non-interacting by a kind of pre-established harmony, they are correlated. So, okay, but now here's the issue. Because, we're used to thinking in terms of local normal Schrodinger quantum mechanics, where we get to treat time as an external variable, and we're free to measure this and then do that and whatever. We have to make a kind of mental adjustment when we think about how things should work in this global picture. Some of the interpretations of things are going to be a little different. And the important part is that in the global picture, it's all about conditional probabilities, right? So in the global picture, it's like we're going to condition any probabilities that we extract from this theory based on clocks, some number of clocks showing, certain time. So it's like, suppose we take A to be the clock and we say, okay, suppose A says it's, 6 o'clock. We project A into that time state, and then we can be like, well, given that, what's the probability that if we did an X measurement on B, it would be up or down? So rather than just being like, oh, let's measure, X on system B, it could be up or down, and get with a certain probability. It's like in global quantum mechanics, everything is conditioned on what time it is.
When you say project A into a time state, you mean hypothetically what things would look like if a measurement resulted in that time state?
Yeah. Think about it like that. Yeah, totally.
Okay.
So crucially, we're still just calculating probabilities. We have a timeless, so this to me is what separates this from a block universe picture. We have a timeless global state of the universe, but the individual outcomes in the universe are still only determined by probabilities. The actual outcomes are only available to observers in the universe. Like, although the global picture encodes all the information for all time about all the conditional probabilities in the universe, nevertheless, it doesn't allow you to predict any individual outcome.
Are you saying
It's
that?
certainty.
Are you saying that a godlike observer outside of the universe does not see probabilities? He sees a deterministic universe.
Yeah, I like to think of it like if there was a God outside the universe, the God, could know all the laws, it could know all the probabilities, but would be almost like necessarily unaware of any of the individual actual outcomes that happen in the universe.
This sounds like a proof of classical physics, which is deterministic. It doesn't. How do we reconcile this with
the history and the future of the wave function is deterministic, but the wave function itself encodes a probability, which is separate, right?
Yeah, so it's like the quantum states encoding the probabilities, but it's like nature itself, like in, I don't know what you want to say, like the observer's experience or whatever. Like if you might say it's like, I mean, okay, it can kind of get a little hairy, we're interpreting quantum mechanics, but I mean, the way that I think about it is that, definite outcomes in the sense that we normally think about them are observed by, subsystems of the universe.
But bottom line, on a global scale, the whole universe, is it probabilistic or is it deterministic?
I would say in this picture,
it
says that the laws.
No, but what is this theory saying?
It says that the laws are deterministic and the outcomes are random.
But if you were if you were all knowing, all observant outside of the universe,
you could know the laws, but you couldn't know any of the outcomes. No, okay. Like why? Why does it have to be that way?
No, but I'm saying this is what you're saying here, according to this theory, an observer outside of the universe, for that observer, everything
no,
is deterministic.
They would just see this timeless, entangled state, but they wouldn't know, like, did someone in the universe see the spin was up or down? Like, they would just see, like, oh, so, if this happens, then this happens. But if that happens, then this happens. So it'd just be a superposition over all the possibilities. They wouldn't know any of the individual outcomes.
So they would see all the possible superpositions, but they wouldn't know what actually happened.
Yeah, that's my claim.
Which means, bottom line, physics is probabilistic, not deterministic.
No.
That's the way that I look at it.
Physics,
I mean,
events are probabilistic.
Physics, as it is practiced,
well, that's what I
by
mean.
human beings, is probabilistic. We try to determine, the momentum of the particle, and we cannot determine the position of the particle. We try to determine the position of the particle. We cannot determine the momentum of the particle. We're in a realm of uncertainty and probabilistics anytime we're in, as human beings, in the quantum realm. A divine being, I don't believe in divine beings, I'm an atheist, but a divine being would know every single parameter, would know the theory of everything, would know the grand unified field theory, would know the exact nature of dark energy, if dark energy exists.
But that's not what...
Yeah, like a completely transcendental being, sure.
That is not what quantum physics says.
But I think that's not even true, right? Because of that Cohen-Spector theory.
This is not relevant.
Yeah.
That's the whole point. Quantum physics says that physics is probabilistic. It is not deterministic. Classical physics, Newtonian physics, that events are deterministic.
You're working your limitations as a living being, and your use of tools to measure your use.
No. That is not even what quantum physics says. Quantum physics says that even beyond our own intellect,
imposing your limitations.
No, that's not what quantum physics says.
Well, yes,
it's not about our limitations. Quantum physics says that there's no such thing as determinism, that it's probabilistic beyond our intellectual abilities.
You're not going to get this right, so.
I mean, I think that...
Victor, you keep coming back to this, that if we only knew the hidden variables and we were smart enough, then we would know. But that's already been...
It's supposed to be, it's worse. It's worse than not being able to know what all the values are. Is that the values haven't taken on their, their value.
Taylor's theorem says that if you knew all the variables and all the rates of change, you have completely determined the function. So you would be able to predict all of history. That's Newtonian physics. Quantum physics says, no, that's not the way things work. That outcomes are probabilistic.
Quantum physics takes the error which is based upon the act of observation and makes it into a principle of the universe. It is itself a philosophical error.
No, well, that's your opinion.
Look,
Most physicists don't agree with that.
I think it's like there's two perspectives which are both necessary and which like in themselves can't be reconciled. Like one is that, if you try to take a global picture of the universe, like as we're saying here, that follows quantum mechanical laws, you get, this sort of, there's like a kind of determinism to it. This wave function is given, for all time, etc. But that's not to say that the experience of local observers or subsystems of the universe can be reduced to that global state.
But you're assuming, Matthew.
And I'm not saying that like it has anything to do with human beings.
You are assuming that
the part of the universe is different.
You are assuming that the wave function is eternally unitary. And as soon as there is an interaction, whether it's a measurement or any kind of interaction, that collapses the wave function probabilistically. And it's no longer unitary.
Yeah, so like, interestingly.
This is why what Victor is proposing is not valid. Victor has a Newtonian view of physics.
No, what you're saying is by definition not valid because you're basing quantum mechanics on the change in the system brought about by observation, which itself alters the system so it no longer reflects the nature of things.
Doesn't have to be observation. It's decoherence. Decoherence is probabilistic.
Quantum mechanics gives us more or less accurate probabilistic forecasts of what are going to happen in a system, but it alters the nature of the system to do that. And so it is not a reflection of the nature of things. It works the error of observation into an entire understanding of the cosmos. This is the most immense and risible philosophical error.
Victor,
like, what do you think about relationalism?
John
relationalism
Bell
as a whole.
what you're saying.
This is too philosophical.
Okay, wait, let's put a pin in this for just a second.
You should do like an office hours recitation hour, like midweek to talk about it.
I got like just a couple more paragraphs, and I do a little philosophy. So like, let's just put a pin on this for like 1 second, and then come back to it. Okay. So this is about like what we have to do, the kind of mental adjustment you have to make when you try to think about quantum mechanics globally. So, if our global picture is really global, it's like we're talking about the universe as a whole, right? So it's like it's got us in it, it's got the systems that we measure, it's got our apparatuses, it's got our measuring devices, it's got our memories, and it's all encoded in this like entangled superposition, all the different choices of measurements we could make, resulting dependencies, all the different outcomes that the system could give, and then this happens depending on this thing and this thing and this thing, and it's all represented in entanglement, which represents the dependencies of one choice in the universe and another choice in the universe. The whole structure of possibility is encoded here, but arguably the state encodes none of the definite outcomes. The observer is just as important as the global state itself. The global state gives probabilities with reference to different observers in the universe, and this is the important point, while being independent of all of them. So the point of using like a global wave function is precisely to describe the world independently of all observers. And it's then like, at the end of the day though, we are observers, and so we then need to, try to recover our experience as being an observer from this picture. So we can't just think about like, let's measure this global wave function and project it and do a measurement. No, that's not how it works. We're not doing any measurements anymore. You can't measure the global state of the universe. How can you measure it? There's no measuring apparatus outside the universe to measure the whole universe, okay? And even if there were, you project, you know, like this global wave function in some state like you measured it, there's no guarantee that that's going to be in the zero energy eigenspace of the energy operator. Like it could be the case if the operator that you're measuring commutes with the energy, but like that's not guaranteed. So like when we normally think about quantum mechanics, we're sort of like, well, you know, we make a choice about what to measure, and then nature makes a choice about what outcome to give us or whatever. And then on the basis of that, we can then choose to make this measurement, right? And then we get a response, and then we can condition what we do on what that said. And it seems like in each case, we have this like sort of freedom. Like we have the freedom to choose what to measure, and then the system has the freedom to respond. That is like not how you should think about the global picture of quantum mechanics. It's like metaphysically, like you can't change your mind anymore once you've created this description. Like if we later decide we want to make a measurement in this universe, we can't. Like in other words, we need to construct a different universe that contains a measuring apparatus with the right Hamiltonian, so that it's like entangled with a phenomenon, so that the states correspond to the correct reading of the instrument.
You know, Matt, when you say measurement, you're implying an observer.
Yeah.
What you should say is wave function collapse, which doesn't necessarily involve an
Well, I'm
observer.
saying there's no collapse, no measurement, no nothing.
An interaction. When we say measurement, then we're relating it to an observer. We should say any interaction results in wave function collapse.
Oh, I see what you're saying.
And the result is probabilistic. It is not deterministic. This is what characterizes quantum physics versus Newtonian physics. Newtonian physics said you could measure all the variables and their rates of change, their derivatives, at any point in time. You've completely predicted both history and the future.
And
quantum physics says no, that's not the way the universe works.
And then you keep repeating the received idea of the error and the alteration of the system, which is based upon the observation, and pose it on the entire universe and make it into a law of the universe.
But Victor,
Victor has a point.
Is Newtonian
I think this is an interesting conversation, but I think I get the sense we should wait to have it.
Okay, let's.
You know, I don't think. I mean, I'll say this: like, I have no reason to believe that quantum mechanics is the final theory of reality in any way. I mean,
but it's closer to reality than Newtonian physics.
Yeah, I would say that, but you know, so my point that I'm making here is that, you know, there's neither collapse nor an observer, you know, outside the universe. Okay, so it's like if you're considering the global wave function, there's no measurements on that thing. Like there's no collapse at all, because there's nothing outside the universe to like collapse it or whatever, even if it's, you see what I mean? So what you get is like just something that lets you calculate conditional probabilities for an instant of time, given that some things happened. In other words, in the standard local picture of quantum mechanics, we regard the experimenter as free to choose what to measure. Nature is free to respond to the outcomes of the, free to respond in its outcomes to those measurements up to probabilities. You can think about it like the global picture is obtained by giving up the freedom to choose what to measure. Instead, all the choices you could make, all the branching evolution is encoded in the entanglement timelessly in the global state. But nature still has the freedom to choose the outcomes. Indeed, the global theory only predicts probabilities for what local observers observe.
But then, what if you have like I guess it would have to be encoded originally in the construction of this universe. If you have a situation where the outcome of an actual measurement is what you use to determine what to measure next.
Yeah, so you can do that, but it's like once you've constructed that universe, you can't change your mind.
Right, but it was sounding like the choice of measurements to do is all predetermined, but their outcome is not.
Right, so what I would say is that the global state encodes the dependencies between the different choices that can be made, but I would regard the experimenter's choice of what to measure and also the, you know, the choices made by nature, the particles or whatever, to be the same thing. Like they're both these random outcomes. Sometimes we make them, sometimes electrons make them, and those are the things that can't be predicted with certainty. Those are the things that depend on being a part of the universe as opposed to like the whole universe.
And also,
But just
Matt, once you have decoherence, wave function collapse, or if you want to call it a measurement or an interaction, you start all over. You don't know what the original initial conditions are. There are new initial conditions.
Not in this
And
case.
you can
No,
never
it's
go
like
backward in time. You can never go backward in time to figure out what the initial conditions were.
Right. So for like an observer in the universe, yes, it's like once decoherences happen, it's going to be incredibly unlikely that you're going to be able to like find all those gas particles and, you know, undo the ridiculously complicated quantum, you know, evolution that spread the entanglement of your system throughout, you know, everything that it touched, leading to decoherence. But I mean, if you're taking the global picture, remember, the global picture does not depend in any way on time. Time emerges in the universe. And so, you know, if you want to take the decoherence perspective, I'll actually put a paper. There's a great one by Hartle, you know, of Hartle and Hawking fame. And, you know, he talks about decoherence in the sense of finding like, so he'll regard like you have like the global state of the universe, and then a particular history is given by a series of projectors. And ultimately that can give you like the probability that a given history is observed. And then the idea is that, you know, some of these histories may or may not be orthogonal. And it's only histories that are orthogonal that can be said to have probabilities with reference to each other, and so correspond to decoherent histories. Like this happens with this probability, this happens with that probability.
How should we think of causality in the context of timelessness and sort of something taking on an entire history instantaneously upon measurement?
So similarly to like the case of like where we just have two spins that are entangled, right? For every state of spin A, we have a state of spin B. So like that's the timeless part, like that's the entanglement. It's just like a dependency, a relationship between A and B. The thing that's yet to be determined is what A actually ends up being. And then once that's determined, which is like one of these like, you know, impossible to predict things besides probabilities, then you can be like, well, then if A was this, then B is that. So the thing that's timelessly encoded is the dependencies, and the thing that emerges for individual observers are the outcomes. And these outcomes depend on each other.
There's another way to look at this, Matt, that you can know you can know everything about a quantum system, but know nothing about its subsystems.
Yeah.
That's another way of looking at this.
Yeah, no, I agree. Sorry, just looking down my phone.
But decoherence or measurements are all probabilistic. It's not because we don't know what the hidden variables are. That's already been disproven. It defies our common sense.
So there was a recent paper, I think, Science, maybe in the last few years, about it sort of all hinged on the idea that, like, I'm only mentioning this with the hope that someone else knows it better than I do, but like the results that go on in one lab, like someone is looking at an entire lab as a quantum system from the outside, and they're in their own lab looking at the first lab. And within that first lab, there's a measurement going on that the scientists in that lab are looking at, and they're seeing themselves as the classical observer of the quantum system. And they construct some scenario from that points out some deep trouble for anyone who wants a simple picture. But I kind of remember reading that and thinking, I don't know that there have been really well-established rules about like these hierarchies of, there's collapse inside that first lab, but still because someone else is capable of observing the lab in its entirety, somehow coherence has persisted despite the internal first lab measurement being done already.
So it's like,
is this at all, I mean, is this sort of related? Because it sounds like.
Absolutely, yeah. So, I mean, what we've done here is like, we've said, in our normal picture of quantum mechanics, we have the classical time variable t. And, you know, depending on that, we like condition, we like, oh, it's 3 o'clock. Let's check out our quantum system, do our measurement then. Or we could check it out at, you know, 7 o'clock. What's the quantum system then? But that the global picture encodes that as entanglement timelessly between the clock and the system. Now, you can make the exact same argument for any kind of quantum measurement. So like the classic thing is to say, well, like you know, again, scaling this up to how it plays out for like a human observer is an interesting question that we have, it's delicate. But it's like, in principle, the idea that people have is that, you know, I make a choice. I'm going to measure the Z operator on my spin, and I get up or down with certain probability, and then, you know, then I observe that, right? And if someone was like outside this lab and had no idea what was happening, they would describe this not as, oh, collapse, projection, get this, that probability, blah. They would perceive it as an entangling operation, a unitary operation between the observer and the observed that entangles them so that if the system was up, the observer sees up. And if the system is down, the observer sees down.
But a measurement disentangles an entangled pair.
Yeah, so like if two particles are entangled, and then, you know, you measure one of them, which leads to maximal entanglement between those guys, entanglement is monogamous. So two quantum systems, like if these are maximally entangled, then it can't be entangled with some other guy. And so that would break the original thing. But they could be all partially entangled. So, I mean, you know, if you had an imperfect measurement in a sense, then, I mean, you could have more flexibility there.
What do you think about the notion of, when you talk about, in one sense, you can talk about two systems that you know can exist independently, and that you can so-called entangle them, let's say, by putting them together and letting them, you know, wrestle for a while, and then they're entangled. But that what comes out of that, you can not only have to think of it as two wave functions that are entangled, but it's just now a wave function that has all the, you know, information that is equivalent in the picture of the two separate things being entangled. I mean, so essentially like the particles spin up, spin down, that go flying off in different directions, that are so-called entangled. That's like one huge wave function that when one person measures, let's say one, and I guess in a sense the question is, can you really measure just one of the particles? Or are you measuring always the whole wave function? You're forcing the entire wave function to collapse no matter how big it's gotten. And the other person is just going to see the corresponding result. And if you measure off axis the other particle, you're getting, well, I don't want to make it more complex than it needs to be.
So if the particles, if they're separated, then, I mean, if you're just local
like,
to the
can you
one
really
particle,
talk about an entangled, like two entangled particles as two things separated?
So
or is it not really just a wave function that fills that space?
If they're separated, then like you can only measure like the one part that like is near you. But as we've seen, to like make that measurement like affects the overall wave function of both of them, right? Like if you're modeling it like a, you know, I'm measuring it and from my perspective, so it's a collapse, then I mean that steers the other guy, you know, wherever he may be.
But let's say that if like you take the simple case where we're always measuring on the same axis, like always z axis, so that, and it's a, you know, a spin 1/2 particle, so that if when I two spin 1/2 particles in a total spin 0 state, they go off in different directions. I measure spin down. It's guaranteed it's spin up 100% the other, because we're both agreeing to measure only z axis. It's when you go to like you're going to measure with some angle with respect to z in the other lab, then now you can get sort of like new surprising, you know, unpredictable. But the sort of you could say that was a total that the particle that went to the other lab where someone decided to measure off the z-axis was actually in 100% up z direction, and then they decided to measure, you know, 30 degrees with respect to the z-axis, and you get what you always get in that situation when you measure. It doesn't matter if it was previously entangled or not. You measure something that was born in the you know, up z state, and you measure it not on the z-axis. You get, you know, unperceivable, you know, distribution of result.
So the probability in itself is like, you know, to the extent that things can be in like you know, if you have a particle, you know, that's expected spin axis is around the z direction, you measure along the x direction, you know, it's going to be 50-50 up or
Right.
down, whether it's entangled or not. I mean, just by
Right. So I guess in a sense,
geometry
one
of the-
lab measures one of the paired particles, does that measurement. That other particle that's still out there, yet to be measured, so to speak, does it really need to have been part of an entangled pair to have the properties that whoever measured it is going to experience? Can you not just sort of create that same particle from a non-entangled origin? Because the entanglement's over really once you measure. So because if the answer is yes, then it's kind of like, it seems like you have this huge wave function that represents the entangled pair, that when someone does a measurement on so-called their particle, that whole wave function collapses completely, and that other particle, which is now no longer entangled, goes about its business, and you could do measurements on it, and it doesn't really matter that it was previously entangled.
Yeah, no, that's totally true. That's totally true. And then if you think about like the global wave function picture, it's like, yeah, whether the two particles are entangled or not, well, it depends on what time it is. So, you know, if you measure the clock at this moment, you know, like before they've interacted, you know, they're, you know, unentangled, and then maybe you measure the clock at this instant or whatever, you condition on the clock showing this, and then now they're entangled because they were interacting, and then, you know, condition on this time, you know, the measurement took place, and like now this thing's entangled with this measuring apparatus, and these aren't entangled anymore, and then at this instant. So
I wonder if part of the, you know, sometimes you wonder like where the challenge with having it feel intuitive lies in the difficulty of getting good language to, you know, to capture the concepts, and how much of it is like intrinsic to the weirdness of reality.
Yeah, but, I mean, our language kind of sucks. I mean, that's why you need the math, because it's just
right.
Like,
so, and it's kind of
verbal.
my motivation for bringing this up, because if maybe there's some sort of artificial confusion, you know, or difficulty with understanding something intuitively, to be talking about two things that are entangled, because maybe it's better to talk about it as this one thing that was maybe formed from two separate things, but by mixing the notion of two separate things with this condition of entanglement, you're kind of mixing two pictures of two separate things and one unified thing in some sort of half form. But maybe it's cleaner to talk about, you know, you form this new object, you know, from two particles. It has this wave function very well defined, and it evolves as, you know, Schrödinger equation. And to talk about it that way, and sort of resist the temptation to think of it as these two separate things that have all these sort of rules attached to it.
Yeah,
They're a single system if they're entangled.
Yeah.
And when you make the measurement, they're separate systems.
Right.
Are you planning on ending strictly at 6 o'clock, or are you planning?
No, I'll keep going. Yeah. No worries.
Okay. Well, then for like what, 10, 15, 20, what?
Well, you'll put it on YouTube, right? So if you want to watch the.
Yeah, if you have to go, you know, I will put up the recording and everything. Yeah,
no, I just was wondering because it was 6 o'clock.
Yeah, I just put 2 hours like for no reason. Yeah, we can go.
The very first time that I sat in, which was a month or so ago.
Yeah, we went quite long, I recall.
You're talking about entanglement. You were talking about wormholes. You were talking about Hawking radiation. You were talking about also about specifically with high seriousness, teleportation.
Hell yeah.
And you were talking about going beyond the teleportation of particles, the recent experiment with China, between two particles that were 300 some odd miles apart. And you actually talked about the possibility of human teleportation. So I wanted to go back to that because it was one of the very first things that you spoke about. And I'm sorry to interrupt the discussion, but there was a study that was, first of all, there's, in the most recent estimate, there's 37.2 trillion cells in the human body. Beyond that, there's all the microbes that live on our nerve endings, on our skin, and in our guts, which are actually larger in number than the number of cells in our body. So a study that was done at the University of Leicester said that teleporting a human being would require the transmission of 2.6 times 10 to the 42 bits of information. Now, this would require, in present day terms, energy terms, 10 trillion gigawatts of power, which is the entire UK power supply for more than 1 million years, and would take, at the current rates of transmission, 4.8 million years to transfer the human being, which is 350 times longer than the
Wait, Victor,
You're better off just taking a car.
slow down. What were those numbers again?
What's your point?
No, I mean, I think that's exactly why we have cars and bikes and we walk
Yeah.
around and are like teleporting everywhere. It's like for exactly that reason. It's very
Teleportation,
expensive.
Victor.
Exactly.
Teleportation is
To
not
work.
about teleporting material objects. It's about teleporting information.
No, you can teleport material
Not be
objects.
teleported like they did on Star Trek.
I
No, you totally can. You can teleport.
I am
Teleport.
addressing the fact that Matthew took seriously the idea of teleporting a human being, and I don't quite
you
do
can
that.
Well,
because
okay,
I-
That's
wait,
okay.
can I respond to
You
that?
can
Can I respond to
teleport
that?
bits.
That's
You can't
okay.
teleport objects.
You can definitely teleport objects, but here's
No.
my thinking. Right?
Ever heard of the no cloning theorem? There's a no cloning theorem. You cannot recreate. You cannot.
Well, you destroy
If
the system and then
If
reconstruct
it's
it
in a
later.
definite state, you can teleport.
Yeah, you can
only
teleport.
You
Look.
you can recreate your body, but it won't be you.
It would be because it would be entangled in exactly the same way. It would be indistinguishable.
You can only
So-
teleport information.
you would have
No, you
to
can teleport a qubit. That's the whole point. So
you can teleport qubits,
Here's the thing.
not material objects.
the reason I brought up the question of, can humans
Qubit
be
is a
quantum
material
teleported?
object.
No, it's
Yeah,
not.
exactly. Yeah,
It's
it is.
information. You can teleport information.
It's the angular
teleport
momentum of a
physical
quantum
object.
particle. That's what a qubit
There's
is.
something called the no cloning theorem in quantum physics.
You're right about that.
But that has to deal with if you don't have a definite state. If you have a definite state,
You can teleport the state. We can teleport Victor, but it wouldn't be Victor. It would
well,
have the same
that's get.
information as Victor.
Let's talk about something like a qubit or something like that. If it's in a definite state, then you can teleport that qubit because
you can teleport the qubit. You can't teleport the object.
You can even teleport a qubit in an unknown superposition. And it's not
Yes.
cloning.
The problem is you would have to teleport every single neuronal firing.
come on.
Absolutely.
Come
No,
on,
wait,
stop
Victor's
talking
completely
about-
right. He's completely right,
That's
though.
just a technical issue, but that isn't the point.
The
you
reason
can't teleport an electron.
The reason I brought it up is
You
because
can
I
only
wanted to
teleport the
distinguish.
information.
Hey, the reason I brought it up is because I wanted to distinguish the wormhole case from the teleportation thing. Because arguably, it's the same idea, like at a conceptual level. But whereas in the case of teleportation, it is really quite extravagant to imagine that we could take a whole human body, make these like measurements on every single one of our gazillions of particles, write down all the ones and zeros of those outcomes, send it over, via text message to somebody else that determines a particular unitary operator to apply to this, entangled particle that they have over there. That's like, one of the.
But it wouldn't be you.
Etc.
It
But
wouldn't be
okay,
you.
but that's a separate issue.
I agree.
The in the wormhole
fully-
case, it seems more plausible because there, it's there's no need for like a collapse and then an error correction, so to speak. It's like you have now basically a notion of just literal geometrical connectivity.
A wormhole
you
just
just-
means two black holes
You
are
just
entangled.
go through. Yes, you fall in the one black hole and you pop out the other one.
No.
In other
But
words,
the thing is, you couldn't keep
experience-
the opening. You couldn't keep the opening open long enough for a material object to go.
You
through.
could. So they've proven that you can.
No, they've proven that you can't.
No, they've proven that you can. You can when
So
you
here-
incorporate
Maybe for an
quantum mechanics
electron,
into
but
the
not
thing.
for a human
What's
body.
the name of that result?
Anything.
Here was the second. Here was the second.
Look up
issue.
traversable wormholes. I mean, it's agreed upon that they exist. They're possible, and they could be constructed astrophysically, and we can use them to analyze like
So how do you?
non-logical systems.
So why wouldn't you be destroyed before you get teleported?
Well, so I mean, it's like
Destroy
you would.
the singularity.
The idea is that like you would experience falling into the black hole, traversing some kind of weird geometry, and then popping out the other black hole.
But you'd be destroyed. No, you can't pop out.
You
can't pop out.
You can, because the black
No.
holes are going to be coupled. They're going to be interacting.
But you can't
holes.
pop out of a black. You can't pop out of a single black hole.
You can,
It
because
would violate
the coupling.
relativity.
No, because the coupling between the black holes from outside looks like a negative energy coupling from the inside, which actually translates the person who fell in such a way that you can think about it like, it's not that they can pop out of the black hole, it's that for them, the event horizon is actually moved back. So they end up just outside the event horizon on the other side.
Didn't Kip Thorne say something about that?
Say it again?
Didn't Kip Thorne write something about that?
They may have. So, I mean, this stuff is largely, the last 20 years of
If
research.
Alice and
This has
Bob
become-
jump into their respective entangled black holes, they can meet, but they can't report it to the outside world. They can't get out.
The idea is
They
that
can't
they
get out of a
can.
black hole.
So that's the case if the black holes are entangled.
Even
If
if
furthermore,
it's entangled, you
the
can't
black
get
holes,
out.
yeah, if they're entangled, they can meet in the interior potentially, but
Right.
not escape. But if
But
the
you
black
and I
holes,
can never find out about it.
if the black holes are interacting in a particular way, then they can escape.
There was a second thing that I wanted.
That's what we did. We saw it. I mean, dude, we literally saw it. Like I have a simulation that that just like does the algorithm. And you can see, you throw in a qubit,
Where's
and then
the
like a
black
time
hole?
later,
Is there
it
is there a
pops
name for
out
that
the
kind of
other side.
interaction?
I don't know.
About.
There was a
Math
second.
works
There was
out.
this, Matthew. There was a second point that I wanted to make that about an issue that you were discussing the first time, which is about Hawking radiation, and
Okay.
it is very little understood, seemingly, in the general public. You've got a wide portion of the public that knows of the existence of Hawking radiation.
Don't believe it, Victor. It's
and
a
is
fiction.
talking-
Not in America.
and is talking about dissipation or evaporation of the black hole. So here are the numbers. The smallest black hole is 2.5 solar masses. Okay, that is the black hole which decays the most quickly of all of the
Okay, interesting.
black
You can have
holes.
microscopic black holes that.
So
that
now let's
decay
take that black hole.
instantaneously.
Let's try to create conditions to make it possible for the dissipation to take place. Let's move that black hole into intergalactic space, and let's say that there are no stars, planets, planetesimals, dust, gas, plasma that it can feed on. There's not even any cosmic rays. Any
Well, what's the
stellar
point?
winds. All there is cosmic microwave background radiation and starlight. So
Okay.
here is the relationship between Hawking radiation and the combination of only starlight and microwave background radiation, okay? Per second, the starlight and microwave background radiation are 8 times 10 to the 31st power times more energy per second than Hawking radiation. So no dissipation, not even close to net dissipation is occurring in any black hole in the universe that we have observed for there to even be the cutoff point for actual net dissipation to be occurring. You'd have to have a black hole of the mass of the planet Mercury or less. And therefore,
Victor,
That number of
I'm not
8
sure
times
I
10 to the
understand.
31. you
Hawking
said that-
radiation is based on a fallacy. It equates Clausius entropy with Shannon entropy, which
Huh.
a lot of physicists make this mistake, including Hawking. Hawking was wrong, and he even suspected that he was wrong. How many times did he change
Yeah,
his
well,
mind?
these days people agree completely that Hawking was wrong, and what he didn't take into account was precisely wormholes. That
No, but
actually
besides
correct-
Could you fill in a little bit more detail there?
Entropy with thermodynamic entropy. They're two different things.
Well,
And Susskind
no one
also
was saying
does
that they
the
were. It
same
was
thing.
obvious that they were the same. They found that it was surprising that the surface area of the black hole scaled exactly like its entropy.
Look, again, it's not falsifiable. Hawking radiation from a typical black hole in the universe is microkelvin. the crap that circles around a black hole is going to swamp out any measurement we could possibly make of Hawking radiation. It can't be done. So this whole theory is non-falsifiable. It violates Popper's theorem of falsifiability.
Why can't you measure the
Because it's
Hawking radiation?
Hawking
Saying that the power's too low?
A black hole is microkelvin. The crap that floats around it is, humongously larger. How the hell are we ever going to measure it?
I don't know, surround the black hole with a Dyson sphere and just
look,
collect it
It's
all
actually,
out?
First of all,
it's actually
again,
nanokelvin.
the whole theoretical basis for Hawking radiation is wrong, and I don't care how many physicists believe it. It's based on faulty assumptions that even Hawking
the point I was making,
then
Michael,
changed his mind.
the point I was making, Michael,
Yeah.
was not whether it was right or wrong. The point was to
You can't measure it.
talk, just listen for a second.
Yeah.
Point was to compare the
Yeah.
amount of energy, okay, being absorbed by the black hole in any instant, just because mainly the cosmic microwave background radiation, the starlight is far, far less compared to the Hawking radiation.
That's exactly what I said.
Dwarfs
That's
it.
what I said.
1 second.
The background radiation.
One second,
would swamp
one
out-
second.
Let him
Victor
agree
said
with
something
you.
different.
The
1 second.
background
Dwarfs it.
radiation would
Wait, so
swamp
Victor-
out any Hawking radiation.
Wait. So Victor, you're
can't measure
saying, that the black hole wouldn't dissipate because it's always absorbing more than it's dissipating.
Until about 100 quintillion years, the 2.5 solar mass black hole would not begin to dissipate. So you'd have to move into the entropic phase of the cosmos, whether it's the big
Or
chill
you're going to have
or the big,
microscopic
or
black
the big
In
rip,
fact, they were
and you
worried
no
that they
longer
would
have any
lose that
starlight,
galactic
and you're not,
multiplier.
you no longer have any starlight, and the cosmic microwave background radiation has been absorbed by the black hole.
No, I see your point. That's a really
Supermassive black
interesting. I don't know. I don't know enough about the astrophysical theory of black holes, like in a sense, to be able to say anything intelligent about this.
You
But
don't
like,
want to know. It's wrong.
but this is certainly like the kind of reality check that is important to have. I mean,
So is ultimately the claim there just that the
you're
black holes will
saying-
not evaporate because of this
Like,
net, gain versus loss? But
Exactly.
Why did the
that's not a
black holes
challenge of
have
the
to be-
Hawking radiation existing.
I made that point in the Manhattan Quantum Group, and at least one person who's not here with us today absolutely dismissed the idea. I said that every black hole in the universe currently is accruing in mass.
Wait, but I don't
It's
see what
absorbing.
I feel you, but like I don't understand why do you need the this big black hole with all the solar
They're all
masses?
accruing, and if there is Hawking radiation, it's dissipating at an.
But I don't understand that. Why can't I just make a tiny little black hole like in a
Right,
big
you can make a tiny black hole.
lead container or something? Like, why
Listen,
can't I just?
But
Plus-
are you talking about the limit of, I don't know, Schrödinger limit of like, if something's going to form a black hole by collapsing, you need a certain amount of mass to begin with.
Plus,
But as far as
predicted
like
black
holes,
Plus
predicted black holes, 200
Can we just all like one person talk
Yeah.
at one time?
You could still
Laplace
get a
predicted
neutron
black
star.
holes 200 years ago, and he said nothing can escape from a black hole. And that's as true today as it ever was. And all this bullshit theory about black holes radiating is just bullshit. It's based on faulty theory. Nothing
Whether or
can
not
escape from a
it's
black
true
hole.
is not what I was addressing. Whether or not it's true is I was addressing whether there are black holes that are dissipating even if Hawking radiation is underway from each of them at a greater rate.
Not the ones we
upon
know
the
about, but
solar
we can produce them in the
radius.
lab.
Wait, but Victor,
can
so
produce-
you're concerned with why can't you have a tiny black hole?
Right, and which could be produced in the lab.
Well, in our observations thus far, the 2.5 solar mass black hole is the smallest. Over time, if we still have, for instance, nano black holes from just after the Big Bang, assuming there was a Big Bang, which I don't assume. But
We could produce them at the
Okay.
LHC.
if
We could
we
produce
still had some
nano black holes at the Large Hadron
then
Collider.
they could be currently dissipating as long as the mass is less than that of the mass of Mercury. Then the net dissipation would take place in relationship to the accrual of mass due to the accrual of particles, energy particles and matter particles.
Right, so you're saying that there's no reason to believe that any astrophysical black holes will in fact dissipate in the way that Hawking argues.
Not an hour
that might apply to tiny black holes, but
No, it will
those
take a
haven't been observed.
No, it will take over cosmological timescales, they will begin to dissipate. When we move into the big chill or big rip phase of a cosmological scenario.
Because the background radiation is going to cool eventually enough. That
exactly.
Yeah.
I mean, there's papers that like use I mean, they model these things like the Hawking radiation, you know, in terms of like.
They model it.
I mean,
but it's
actually,
wrong.
one of the you should watch the this lecture that I had posted in
by the Chinese woman.
Yeah. She gives like a quantum computational model of like black hole evaporation. You know, it's not quite different from, you know, kind of like a thermal bath, you know, kind of idea. I'd be curious what you would have to say about that. Okay, I mean, I guess the last thing I wanted to say, like here in the notes, is just that it's just like a metaphysical point, right? We have this idea of a global state or like whatever we got there through some philosophy or whatever. But how realistic is that really? You know, is that just a failure of our imagination? You know, the whole universe has a law which never changes. Is Leibniz actually right? I mean, what if the laws could change, you know, conditioned on our choices in some weird way? You know, is it an ontological fact that there's a global state? I mean, because after all, we observe in our universe subsystems like a Kitaev system with the clock and the whatever, that can be in a zero energy eigenstate. So it's timeless with regard to us. And so from the perspective of that system, we're kind of like a god, you know, standing transcendentally outside it, in the sense that, you know, for them, we exist kind of beyond its history, which for us is simultaneous. And so how do we really know that any given universe isn't just some zero energy subspace of some larger universe, you know? And if we try to embed any given universe in a larger universe, you know, do we imagine the larger universe was always there? Or, you know, could the universe have grown in some sense? In other words, you know, we could imagine an ontologically complete global state of which we're necessarily ignorant. So that our choices and everyone's choices, whatever, are quantum outcomes rhyming in accordance with some eternal timeless law. Or we could imagine that the universe is constantly growing in some sense, changing its law. Although logically, from within the universe, you'd never know that the law had changed, since it would appear like it had always been that way. So in a way, it's asking a question: does the universe have an eternal memory, or can it change in unaccountable ways, bringing novel things into being? And I don't have an answer to that.
Collapse of the wave function destroys unitarity.
Well, but this has nothing to do with
which destroys eternal memory.
This has, well, no, it wouldn't, right? Because if you're working in the global picture, like that measurement or whatever is just a relationship of entanglement between a measuring device and the system. And so from the observer's perspective, yes, something has been lost, but from the perspective of the whole, nothing is lost. I mean, that's the whole point of unitarity.
So you never have collapse of the universal.
Yeah, no collapse of the universal wave function.
But by the same token, you cannot know what's going on in the subsystems.
Yeah, yes, that's my.
So the whole thing is ridiculous. So you have this godlike outside observer who doesn't know what's going on.
If the mind of Isaac Asimov arrives, if arrives in the
he died before John Bell.
If he arrives in the instant at an understanding of the theory of everything, then the wave function of the universe will collapse.
What?
I'm only joking.
Oh, that's a
Richter, Richter, turn on your video.
When I say that there's no collapse, again, it's just from this global perspective, right? Like if you think about, like, if this is literally a time independent state, like there couldn't be a collapse. Like if we're like regarding it as like literally fixed for all time.
No, but
but there's no observer for that.
Yeah, there's no observer for the whole thing. So it's irrelevant. It's like the global perspective is just what all the observers in the universe agree on.
Matt, if energy is
could
constant,
agree on.
Matt, if
obviously people
energy is
disagree.
constant, and energy and time do not commute, then time has to be real. Energy and time can't both be constant
Yeah.
because they are non-commuting variables. So if
Well,
you're
revisiting an
Totally.
earlier question about the notion of time being an operator or not, sort of, maybe it's just me, but I don't feel like we kind of really settled that, because in Schrodinger quantum mechanics, time is not an operator, and it's not even really accurate to talk about it commuting with anything or not.
You can have an alternative formulation where it is, but the point is energy and time do not commute.
Yeah, and it's precise.
If one is constant, if one is constant, the other one has to evolve.
But the framework in which time is an operator, is there a name for that I could read about more?
Yeah, so that's the case in this global picture. And the idea is that the time operator should be regarded as the time operator of the clock. And so, you know, you have this time operator that acts on the clock, and its eigenvalues are the different t's that are the classical variable for the Schrodinger equation in the original local picture. In other words, it's like saying, like, if I was the clock or whatever, then, you know, the time would be classical for me. And so I would just see the system evolve in time relative to that classical variable. But if I take an outside perspective, instead this temporal relationship is given by the entanglement between a clock and a system. And the time operator is that, you know, that is relevant here is the time operator of the clock. And so the Fourier transform of the energy operator of the clock, and it parameterizes the states of the system, the other system that you're interested in.
And am I at all near the ballpark when I talk about, like, if you start with Schrodinger quantum mechanics, and which does not have time as an operator, but it sort of implies a single observer is being relevant. But then you try to extend it to include all possible observers, that somehow in that process, time becomes an operator in trying to do that extension?
Yeah, once you start including the clock in your picture of the universe, as opposed to treating it as some external thing, then you get this effect, yeah.
But like, let's say because it sounds like time is sort of unavoidably going to become an operator if you try to do enough thinking, you know. That's what I'm trying to get at. Like, what is, at some point, time is going to be forced in there or not? Because if it's sort of an arbitrary choice whether or not to make time an operator to achieve this perspective, then it seems like an unnecessary, confusing
it's
choice.
Just, again, the Page-Wooders argument is just that if you have two separate Hamiltonians, two separate energy operators, and then you demand that the overall universe is in a zero energy eigenstate, and if you take the Fourier transform of those energy operators, you get an operator whose eigenstates parameterize the other system as if the first one was a clock. So it's not like a choice of time operator. The time operator is completely determined by being like the Fourier transform of the system's energy operator.
Right. I guess I didn't mean, you know, a choice of a particular operator, but just time being promoted to operator status. Because if there's that, I think of, like, I can do a time measurement on something, and there's going to be all the uncertainties.
Yeah.
Whereas before, it's just sort of like, you know, that if there's a definite state, then it's a definite energy, then it's a sort of it's a fixed timeless state, or you know, fluctuations in energy correspond to how long lived they are. But in that relationship, time is not an operator. But I was just wondering, sort of, how unavoidable is it? You know, at what point does time become an operator, whether you like it or not?
Let me try to clarify it using a simple example.
Okay.
Consider just Newtonian mechanics. I go to a soccer field with a soccer ball and I kick the soccer ball. Newton's equation tells me exactly the trajectory of the soccer ball. At any instant in time, just by looking at the clock, I know exactly where the soccer ball is. Or alternatively, I can put the clock aside and I can look at the ball And simply by observing where the ball is, I know what time it is.
Right.
This is sort of a very simplistic illustration of the duality or entanglement between time and the physical world. Now, when we talk about the quantum mechanical world, we cannot say that time is entangled with two different systems. There's a theorem that does not allow full entanglement with two independent systems. So in quantum mechanics, if I have two electrons and I say that time is entangled with both electrons, this is not allowed. But what I can have is I can have an entanglement between time and the entire universe. And in this sense, suppose that at the instant of the Big Bang, I knew exactly the wave function of the universe. And suppose that it satisfies Schrodinger's equation. At any future instant in time, I can just look at the clock, I see what time it is, and I know exactly the state of the universe. Or alternatively, I can look at the state of the universe, and from this I can deduce exactly what time it is. In this sense, the two of them are entangled. One will give you the other. Actually, what this tells you more specifically is that the entire universe is constantly computing its own state. This is the computer that computes the state of the universe, and you cannot do any better than this.
But Moshe,
Now,
Moshe, as soon as you have an interaction, everything changes because you have wave function collapse.
Well, but I think the relevant thing Moshe is trying to say is that, like, this is even the case in classical mechanics, that it's like, you know, you can choose to parameterize some classical system, for example, with some arbitrary variable that you're going to call t or whatever.
Yeah.
But
this is like integrable or not integrable. Right.
Case in classical, but it's not the case in quantum.
So this particular phenomenon is the same in classical and quantum mechanics. It's just the difference between using some arbitrary external variable to like parameterize states of the system versus using a state, like an object like within the system. You know, like even in Newtonian mechanics, like you could have a model of like a clock or whatever and also a system. And the idea is like you could parameterize the states of the system by looking at what the clock's doing, or you could just like look at them both together and choose some like arbitrary variable with which to parameterize their joint evolution. And the idea is it gives you the same answer. So it's just a question of like, are you modeling the clock itself? And it's relevant for relativity reasons because the idea is that our choice of clock is supposed to be arbitrary in a way.
Okay. So perhaps I'm taking too seriously or worrying too much about the notion of operator status for time. It's not because to me when something becomes an operator, it takes on some sort of you say ontological qualities, right? It becomes this thing that I have expectations about what I can do with regarding it, and I understand the sort of the orbits. You know, you can look at where Mars is, or you can know what time of year it is and infer where Mars is. But something becoming an operator, it means like operationally, I have to sort of now worry about like you can put the letter T in an expression in front of E for energy, and vice versa. I don't have to worry about the order. I can't do that with X and P.
Yeah.
So just in my mind, when time is I'll back off. Like when time becomes an operator, it's no longer just traditional Schrodinger quantum mechanics. And I'm not sure what it is because I'm only familiar with it when it's in like quantum field theory or something like that, where you can talk about time on equal footing with.
Yeah, so look up, like the Wheeler-DeWitt equation,
okay.
Time independent kind of global picture. And in some ways, I mean, this is, and also like the many worlds interpretation. I mean, this is why the many worlds people are always like talking about, they don't need collapse. And it's totally true. Like the global wave function or whatever, no collapse. It doesn't even make sense at the level of the
it's a
universe
theory
as a
that's
whole.
not falsifiable, so it's ridiculous.
Yeah.
Well, it's certainly true that the counterfactual possibilities have real consequences in our observable world. I mean, that's what the double slit experiment shows. But whether these, philosophical considerations about, are we allowed to, like, how as human beings, as whatever we are, as parts of the universe, how are we supposed to conceive of the whole? And, we can philosophize about it. You can try to model it with quantum mechanics. But obviously, I mean,
Doesn't seem possible.
are we the whole universe? I mean, can the part contain the whole? There's two questions here, right? There's a physics question and there's a metaphysics question. And they're like interrelated, I would say. Okay, like I'll say this. I like how philosophical this discussion got, and it cements in my mind that my plan for next meeting is going to be a good one, which is I want to go into the history of some stuff. So, yes, like the relationship between like this global picture and the observer-based picture. I mean, a lot of the thinking that goes back to like von Neumann. And it's really interesting if you go back to read his book, like The Mathematical Foundations of Quantum Mechanics from 1932, which is regarded as having put the theory, kind of synthesized what Heisenberg and Schrodinger and Dirac all did, and put it on a firm mathematical basis. Towards the end, he has a whole discussion about the interpretation of, sort of like what we alluded to before, that, from one observer, they make a measurement, there's this projection and so forth, but from another observer's perspective, that's sort of an entanglement between a measuring device. And he makes this point that, what makes quantum mechanics so great is that even as it demands that all conclusions be grounded in a certain observer's perspective, it simultaneously says that the laws of physics are precisely independent of any observer. In other words, the laws of physics are such that you can actually draw the borderline between the observer and the observed completely arbitrarily, and it doesn't affect any of the physics. But such a cut between the observer and the observed must be made. And he puts this discussion in the context of a concept that he calls psychophysical parallelism. And it's not a term that we use anymore. And what's interesting about it, so I've been reading a whole bunch of books, kind of trying to trace, this is not physics now, this is actually just history. Where does that term come from? And there's an interesting story to tell about in German language philosophy in the late 19th century. There's a story that runs through, a group of philosophers, kind of neo-Aristotelian philosophers known as the phenomenologists. Names include Brentano, Husserl, who, influenced later, continental 20th century philosophers like Heidegger and Sartre, and Merleau-Ponty. And they were interested in this animating question at the end of the 19th century, which was is the world continuous or discrete? I mean, people didn't know. I mean, it was they didn't even know atoms existed. They weren't sure. I mean, there was an argument about it. They thought there was an ether still, right? They didn't know about DNA. And there's a big question, about is reality at its fundamental, basis, little atomic things, or is it more continuous, holistic math? And more generally, there's a philosophical question about what is the proper nature, what is the proper relationship between parts and wholes? A mechanistic classical picture always says that the whole is completely determined by the parts. You have some parts, you put them together, and the whole is the sum of the parts. But there's another conception, which is that you can have a whole which is prior to the parts, and the parts only gain meaning with reference to that whole. And these guys, this was not a quantum discussion or even a discussion having anything to do with the physics. They were interested in it from the perspective of perception. Because they were saying, when I look at something, when I have a perceptual experience, I perceive a so-called gestalt. In other words, I perceive something like you sitting on a chair. And that experience of seeing you sitting on the chair is prior to being analyzed into, you know, you and the chair and the proposition that you're sitting on it and all this stuff. And in fact, those things only gain meaning with reference to like that perception as a whole. Furthermore, they were interested in results from like natural science at the time. Like here's a funny example. They were studying embryos and they weren't sure what to make of the following two facts. This is like in the 1870s, 1880s. You have like, they take a fertilized frog egg, and they let it split, and then they separate out like the two cells. And like one grows into half a frog and the other one grows into the other half of the frog. And they're like, oh, so it seems like each cell mechanically is like predetermined that, oh, this is gonna be the half of the frog, this will be the other half. But then they did the same experiment with a sea urchin. And they had the fertilized sea urchin, and you know, they let it split a little bit and then like shook it to separate out the different cells. And each cell grew into its own entire sea urchin, albeit one smaller than the original, or what it would have been the original. And so people who were interested in this question about what is the proper relationship between parts and wholes suddenly took this to be evidence that in some sense the sea urchin was organically or holistically encoded in every one of its cells in a kind of holographic way, because any one of these cells could each grow into its own sea urchin. Now, today we know that that's not true at all. And today we know that's like this the result of DNA, which we can regard as largely mechanistic. But at the time, because, you know, the philosophers at the time, especially in the German-speaking world, were like obsessed with this question. Do parts determine wholes, or can wholes determine parts? And people were marshaling arguments from physics, which seemed to be mechanistic at the time, arguments from natural science and biology, having to do with embryos, and also evidence from perception and like the burgeoning field of psychology. Now it's interesting to see that, like, so for example, by the 1920s, there's a famous debate between Einstein and Henri Bergson. Bergson was known as like a vitalist. So people who like were firmly of the opinion that wholes determine parts, and that the world ought to be governed by continuous mathematics, continua, and not like discrete kinds of mathematics, often call themselves vitalists, as opposed to people believing that the world is just a big mechanism, right? Vitalists like living as opposed to mechanical, like a robot. And these were the sort of the stakes of the debate. And Einstein and Bergson, apparently in public had this debate. And the whole issue was like, Einstein's talking about relativity and its mathematical representation, but Bergson's talking about something different, which is the experience of duration, the continuous duration of time, which in some sense doesn't seem like it can be in perception analyzed into atoms. Now, I would say that it's like, it was only in such an environment of such intellectual ferment that quantum mechanics could arise at all, because arguably quantum mechanics represents the resolution to this question. And the answer to the question of whether the universe is continuous or discrete, mechanistic or vitalistic, whether the parts determine the wholes or the wholes determine the parts, is actually both. That's the amazing thing about quantum mechanics, and why it convinces me that it's a really good theory. Because it says that, for example, whereas like the time evolution of something is just given continuously by this differential equation, the Schrodinger equation, but that, you know, whenever we actually observe anything via measurement, we can say that it's actually made up seemingly of discrete quanta. We get a particular quantized result for every measurement. And so from one perspective, it's continuous. From another perspective, it's discrete. Similarly, you know, in the case of, you know, two entangled particles, that's an example of where, you know, this global state or whatever it's a whole which is determining its parts. The parts are not determining the whole. There's like something above and beyond the parts individually contained in that entangled state. And yet we know at the same time that, like, due to decoherence and other things, we often experience a more mechanistic world where the parts seem to completely determine the whole with nothing left. And in fact,
that debate seems to leave out, and this is not a new idea, although it's, let's just say, that emergentism is an emerging idea, even though it's very old. You can find it in Aristotle. But there is increasingly the notion from of emergent properties that the whole is greater than the sum of its parts, and which contradicts that basic sort of binary debate that you were laying out.
Yeah, so that's why I like, so I mean, it seems to me that's the message of quantum mechanics, that there's a middle path between, you know, holism and mechanism, between continuous and discrete, between deterministic and free. We have here a theory which doesn't make you choose. And if you think about it, you have 5,000 years of philosophers arguing, you know, it's this or it's that. Obviously, the answer had to be both in some sense. I mean, like, you know.
Or there's something sort of inherent in the formulation of the question that just not going to yield an answer by design.
No one would have thought that, you know, all these things could be, like, no one could have dreamed of quantum mechanics in a sense before it was invented. Like, you know what I mean? It's like, it's not like, as much as people like to talk about how like ancient philosophy and the Upanishads or like whatever, I mean, quantum mechanics is, and certainly Schrodinger et al. I mean, these guys love reading ancient Sanskrit texts. That's known. At the same time, I mean, I've read a lot of philosophy and none of it prepared me for quantum mechanics. I mean, it's just not something people really, it's just not a possibility for the way the world could be that anyone had considered.
There is in Sextus Empiricus, who is the, you know, skeptical philosopher who lays out for us for the first time what Pyrrho said. We didn't have a record of Pyrrho's writings. There is a notion, a very strong notion of probabilistics, which comes out of the tradition of skeptical philosophy in the Hellenistic era. So just the notion, you know, you not only find a kind of precursor of quantum mechanics, but if you read through the 10 principles that outline the entire philosophy of Pyrrho, you have a kind of intimation of I'm not going to call it relativity, but a relativistic view of the nature of things at the same time as you have a probabilistic view of the nature of things. And so it really, you know, as was said in Ecclesiastes, there's nothing new under the sun. Okay. So.
Well, yeah, I mean, you can see Lucretius, the Roman philosopher and poet who wrote The Nature of Things, similarly, you know, can be read as, you know, being a precursor to quantum mechanics in the sense that he's an atomist, like Democritus and perhaps like Sextus Empiricus, I forget. So the world's made of atoms, they're bouncing around, but he says that from time to time, as the atom is continuing on its course, it gives a swerve that can't be predicted beforehand. See, it's a very interesting thing. I mean, it's like,
and how much of the motivation for these arguments was based, like where were they coming from? Just sort of pure rational deduction of, you know, there must have been some assumptions that they took for granted and tried to deduce, or they're just being imaginative about what might be.
Yeah, what was Lucretius thinking? Like, why would he have thought that? I mean,
you're
maybe
talking about the clinamen, right?
Yeah, the clinamen, exactly.
The clinamen,
the swerve,
which is really part of the origin of chaos theory.
Sure.
But is that invoked in order to explain something that otherwise it lacks an explanation, or is it sort of?
I don't know if it was
a logical necessity for some other consistency.
It may have been that he didn't want a deterministic universe. Like, he might have been like, well, if it's just atoms bouncing around, then the universe will be like completely deterministic. So maybe I don't want that. So I have to put a swerve in. Like, it could have been logical. It could have been, he may have been inspired by the same kind of things that inspired Einstein when he was like thinking about Brownian motion. You know, because it's like, at the end of the day, yeah, like a ball drop, like a heavy stone drops. I mean, it's a straight line. But I mean, you look at a dust particle in the air and it's just like,
yeah,
swerving around.
Yeah. When you say look at it, I mean, the significance of experiment, like from Galileo.
Yeah. I mean,
it's a totally different philosophy once you decide that you're not going to accept things without confirmation from experiment.
Sure. Well, I mean, I'm not saying Lucretius wasn't observing the world. I mean, at the time, like, he wouldn't have known like that, like, the atmosphere is made of gas, or which is molecules, and so you can, you know, this thing's hitting this thing and kind of explaining.
Sure, but I guess some of the
So-
principles of quantum mechanics, can they be arrived at by just some logical, deducing based on some
Yeah,
acceptable
so, I mean,
axioms, and then you can arrive at it without even doing experiments to realize that there's a need for some sort of.
to some extent, I mean, like similarly, when people talk about like, oh, you read the Upanishads and they predict quantum physics, what they're saying is that, look, here's a text which thousands of years ago is saying things like, who can observe the observer? How can the knower be known? All you ever know is the object of your knowledge. You can't perceive yourself perceiving yourself because that's a different perception, So yeah, you can just on completely logical grounds come up with that. On completely logical grounds, you'd be like, well, maybe the world's atoms. Maybe it's discrete,
Right.
After all, I mean, the Greeks thought the world was discrete. Well, the Pythagoreans thought the world was discrete, made of whole numbers in some sense, but then they supposedly discovered the square root of 2, an irrational number that lies somewhere on the number line between all
but it's
the
still not
rational
really,
numbers.
in my mind, decided whether or not continua is a reality or.
Lucretius would have known to some degree about the nature of air from Anaximenes, one of the pre-Socratics who had specifically the idea that that air was the arche, and that all things, and this is a rather astonishing insight, that all things in the cosmos are in motion in the same manner as air, and therefore Lucretius would have had a notion of being an atomist, would have had some notion of the fact that he's passing through the atoms of the air and displacing them.
That's cool. Yeah, I'd like to. Yeah, send me a link of that.
Anaximenes is one of the major pre-Socratics.
So my point in bringing this philosophy up is, so next meeting I will try to write up. I'm working on an essay that's kind of like the philosophical prehistory of von Neumann's idea of psychophysical parallelism, and where he's getting that, whatever precursors in the ancient world, but specifically these German language philosophical debates about holism versus mechanism that were very current at the end of the 19th century, beginning of the 20th century, which I would say the terms of this debate and our memory of them was somewhat scrambled and interrupted by World War II, because a lot of these people were killed, exiled. Then there's an atom bomb. A lot of things happen. Academic specialization. There's a long story.
And apparently, Feynman, there's some article the emphasis on technical calculations, how to actually get engineering results out of quantum mechanics, became the primary way to look at it.
Yeah.
From Manhattan Project on, and to go back to foundations and interpretation was de-emphasized.
Well, this is the story. Although I think that partially it's I relate to everyone who was I'm not ready to just throw over all my metaphysical beliefs on the basis of this quantum theory you came up with last year. Give me, you're still talking about in 20 years, call me up or whatever. And so then you see by the 60s, people are starting to breathe the quantum air a little bit more comfortably. Yeah, I think it also has to do with this, which is that a lot of that motivation for people to really think about holism and the idea of wholes determining parts came from perception and the phenomenology of perception. And that part, no one still to this day, arguably, has figured out what to say about that. Now you have quantum mechanics. Now you have this theory which, is can encompass holism, quantum entanglement, great, particles correlated over here, etc. What is that? Does that have anything to do with one of the original things that started off the whole debate? The holistic nature of perception, the perceptual gestalt? Nobody knows. And to do physics, it doesn't matter, because all you need to do physics is just to calculate conditional probabilities. And so you don't need to answer the question at all to do physics, how it relates to perception. Although that was actually arguably one of the things that kind of inspired these thoughts. It was people in the 19th century who lived in the Newtonian mechanistic world who were saying, it can't be true. like, I know what you're saying. Like, I know you have this equation. I know you can explain gravity, electromagnetism, and whatever. Like, I get it. I know. But at the same time, I just don't feel it, because like my perceptions come to me as like a unified whole, where the whole is determining the parts, the things in my perception, the parts of it, even if they can be analyzed into parts, only have meaning with reference to the whole perception. I don't understand how a bunch of mechanical things happening in my brain can give rise to a unified experience of being an individual. So they could have just, that's what they were saying in the 19th century. I get all this Newtonian crap, but I still don't understand how perception works. And I mean, that was like, in some ways, what was driving this debate. And we still do not have an answer. I mean, that's the thing. People will tell you that we have an answer, but we don't.
Almost no philosopher thinks that there's such a thing as a unified I, a unified self. So at this point, and I don't know, does that make us all Humeans? Perhaps, but at this, but no, almost no one thinks that there's such a thing as a unified subject.
Yeah, it's possible. I mean, at the same time, though, I mean, I would be satisfied with an explanation for even my momentary perceptions. Like, you know what I mean? Like, I want a theory that can say, like, oh, well, you know, outside observers say that, you know, Matt, your body is this way, and then from that information, I want to predict like what the world looks like to me, like in my head.
But then you're involving all representations that we form that are sort of useful models.
Yeah,
for just
it's crazy.
Operating
it's so complicated.
Yeah, there's no not necessarily that the way that our brains sort of represent the environment is imposed by laws of physics. It's just, you know, perhaps one choice of others of how beings can sort of operate. But I mean, like whether or not I experience myself as a whole, or it seems like when someone says whole, I kind of think like, yeah, that's how I think of myself. Like that feeling of, yeah, that's the right way to talk about it. That says something about physics. It does, you know, that seems to be, maybe it does, but not no reason to think it necessarily.
Yeah,
it's a psychological mental construction convenience.
Well, I was distinguishing, so like, you know, you can read holism in two ways. Like, you could think about the holism of like me as a unified individual over time. That's one thing. But there's even the holism, you might say, in a single instant of time. Like right now, here I am. I'm seeing you guys. I'm seeing this computer and this half-eaten apple. And the thing is, it's like I'm not seeing them like in sequence or whatever. I'm just seeing it all at once, fit together in one scene. There's a scene, and like I can analyze the parts into scenes, like, oh, that I know that's my computer, and I know that's
constantly
an apple, and I can eat
subdivide the moment so that you can subdivide the moment infinitely. Okay,
yeah, we can just
but I would say that at any moment,
it appears to us as a scene before.
Yeah, but I would say you'd have to be in a pretty simple like white room with maybe one object in it to really be convincing that you are seeing the entirety of a moment. You know, because I mean, there's my periphery, there's my distribution of attention levels. Yeah.
Being aware of everything happening around you. I mean,
but
being aware of yourself.
We assume that one could have just paid attention to this other thing, and it would have felt just as real as a thing I happened to have paid attention to. And if you just imagine all these hypothetical things to have paid attention to, you can reconstruct the entirety of the scene of a moment. And that's some whole. But I mean, in reality, psychologically, it's an illusion to think that we're experiencing wholeness, you know.
Right. It's an illusion.
Right.
It's an open question. It's an open question for me. I don't necessarily think it's an illusion.
It's like a feeling. I don't know.
It could be.
Let's go back to the quantum clock. The quantum clock that they've already developed is able to measure time so accurately that it does not vary, does not begin to vary by a second until 33 billion years from the present moment. So let's imagine that you can get down into the level of the nanosecond, picosecond, the femtosecond, you know, beyond what you are referring to as the moment. Each of those distinct subdivisions of time gives you a completely unique moment. Okay, if you are, I think, living in the physical world is Heraclitean, the physical world is Bergsonian. And so there is no such thing as an instant in time. No such thing.
That's my intuition as well.
Or it could be just the difference between inside and outside that maybe. And
there's a lot of retrospect in perceiving a moment that you sort of, like they do that thing where an LED sort of, something is here, then it's there, your brain fills in the transition, things like that. So in retrospect, you kind of like fill in a lot of pieces of what you perhaps did not observe in an instant of time.
And so the question is what makes this question so difficult is that it's simultaneously two questions. Like one is that like, what is the nature of perception for any observer in the universe? A cat, a dog, a person, an electron, whatever. And then it's like, what is specifically human? And it's fucking hard for us to know because we are humans. We don't know like what's the result of just like, well, that's just our particular way of sussing things out, and like what's universal.
And how much are we doomed to fail because of the constraints imposed by language? The way we talk about it is really inefficient.
Now human perception is not limited to the biological. Now we have, X-ray telescopes.
Yeah.
We can see in all the spectra. Okay, we can basically create prosthesis of various kinds for the various senses. We have access to, we know of animals that have other senses than we do, and we can create instruments to do the equivalent, for instance, to allow us to find our position over the earth by our relationship to the magnetic field, as birds can do, or we could create the equivalent of bat sonar and navigate through bat sonar. So in other words, we're no longer limited to human perception per se. It's all human perception, because even if it's prosthesis, but
you have to map these things into our perceptions.
But sorry, go ahead. I
was gonna say, even beyond the like examples of like sensory apparatuses, you know what I mean? Like you can imagine like, I got this telescope or whatever. I feel like another part of this story is the kinds of perceptual changes that happen when you gain a practice or skill, right? So that it's like, if I don't know math and someone shows me a page of math, it's just a bunch of symbols. But being able to do math is not just to be able to recognize what the symbols mean. It means to be able to like look at the symbols as a invitation to manipulate them, as something which they can be turned over, like something, an opportunity to act with them. Like similarly, like I can play the piano. I have a piano over here. And that means like if you don't play piano, like I perceive music differently from you. In other words, when I hear piano music, I'm hearing it with my fingers. I'm literally hearing it like as what my fingers would do to make those sounds. If you can't play piano, you have a different perception of the music. And so, not just the kind of information that's becomes available to us through like different devices and sensory organs, is relevant, but also how our background knowledge and our skills, which I use the word skill, like as I think it's better than knowledge, because it's not just knowing a fact, it's knowing how to do something. Like, I mean, the phenomenologists are always saying like, this apple is like, it's for you constituted by the ability to eat it. Like I'm looking at it as like all the things I could do with it, with the things I have available, my hands, my mouth, etc. And all those things are happening at once when I'm just like looking at it, be like, yep, that's an apple. It means I can pick it up, I can eat it. It's gonna taste a certain way. All those things gathered together in some kind of whatever that is, holistic experience of perception. And it's like, how does it relate to the interpretation of quantum mechanics? Now, I think you can read von Neumann as suggesting something, and I don't think he really like develops it fully, and I don't think anyone really has. So, next time I will make sure to we'll start the discussion there, because it's relevant to this issue about the like when we're thinking about the global wave function like we did today. It's like, so you calculate these conditional probabilities based on like, suppose this clock shows this time, this clock. And so, von Neumann would encourage you to be like, well, where exactly you regard the borderline between the different systems, between, I'm going to regard this as the observer and like what's outside the observer, is a matter of mathematical convention, because the brilliance is that the theory doesn't depend on that result. But of course, all of us have an experience, which is being a part of the universe and having some cut made. It's like mathematically the cut's arbitrary, but we experience a cut. Like, I'm me, that's the computer in the world outside me, so we get a cut. But the
meaning like sort of like a choice, your choice of basis or coordinate system in an abstract sense is up to you.
Sure. Yeah, it's exactly like that, kind of similar arbitrariness. Like, you have to choose a coordinate system, but any coordinate system could work. Right. Similarly, it's like you have to choose an observer, but any observer could work. The laws of physics don't depend on the observers in any way.
But the cut is arbitrary. You certainly know that at this very instant you are breathing 6 atoms from the dying breath of Caesar, when he said, he did not say, and you too, Brutus, he said, and you too, my son.
Yeah,
okay?
Technon.
And so at that moment, the 6 atoms from his dying breath, you are breathing them in, I am breathing them in. So there is no, and you are an ecosystem. You, as I said earlier, you have more cells, more microbial cells in your body than you do have human cells. So there's no such thing as the human species, just as we talk about a mangrove as being an ecosystem, a wild grassland as being an ecosystem, or a tropical rainforest or a kelp forest as being ecosystem. Each human being is an ecosystem. And each human being is a unique ecosystem, and each of us has a completely different balance of flora in our intestines that is leading us to this health issue or this strength.
It's all too true.
In our health profile.
Amazing.
So there's no distinction between inside and outside. There's no cut between, and Kant tries, with his transcendental idealism to, instead of, the notion of the notion of, immanence or transcendence in perception, to have transcendental idealism, the things in me. A completely new way of seeing the world, a Copernican revolution in philosophy, the things in me. And it's like, and here's the simple way to say, I am in the world and the world is in me.
Nice, yeah.
Okay?
And yet, the unanswered question is, why am I not then aware of the entire universe? Why are there some things that aren't in my perception? Like, if there's no bound, like, I'm not saying it's wrong. It's just saying, like, there's two sides of the story. And it seems like that's true from the physics perspective. Like, the cut is arbitrary, inside, outside, not a thing. And yet, from my perspective, there is a cut because I'm not aware of what you're thinking right now. Why not?
But there's also a sense that there are cuts that are sort of more natural to a given situation than others. Sure. And so, like, the cut between where I'm standing and where the apparatus is, somewhere in between that space, versus like through my torso and halfway into the top of the cryostat, that maybe you could formulate everything that way, but that'd be like a really complex thing to try to talk about. Yeah.
Yeah,
so
exactly.
the fact that it's something, some coordinate systems, the thing looks like a sphere, otherwise it looks like an ellipsoid. There's something that says, let's use the one where it looks like a sphere. Maybe there's some significance to that coordinate system then. But maybe it's just the choice of the question is what motivates the best framework.
If I can interrupt for just a minute. Can I interrupt for just a minute?
Sure, yeah, please.
Before I leave, just 2 questions, Matthew.
Yeah.
First question, what happened to Spencer?
Yeah, where is Spencer? That's a great question. I'll email him. Gotta get him back.
Yeah, okay, because he gave a set of great lectures, and
yeah.
It's too bad he's not joining us.
He came one day, but hasn't been back.
Okay. Another question is whether it would at all be possible to move this Zoom meeting to another day besides Sunday. The reason is that the New York quantum theory can meet only on Sundays. And usually after the New York quantum theory, I'm completely exhausted.
Yeah, I can understand
Too
that.
exhausted to join another meeting, which is too bad because I'll have to join this meeting too. So if it is at all possible, think about it. If it's not practical, then don't worry.
Yeah,
about
I mean, I'm
That's
open to having it on like Saturday, for instance. I mean, if anyone has any objection to that, we could do that next meeting. Have it on Saturday instead.
For me, Saturday would be fantastic.
Okay, yeah, let's do that. That's fine with me.
Okay.
Is that another
Okay,
meetup?
very good.
That's a meetup. The Manhattan quantum theorists.
Yeah, the New York quantum theory meetup group. That's another meetup group, also focused on quantum theory. And
Is there a
we have
different
access to
angle on it, or a different sort of I don't know, feel to the experience?
Well,
like why? I'm not suggesting to merge the two, but what do you get in one that you don't get in the other?
The way
Are they
it
entangled?
works is that the way it works is that for every meeting that takes place, the most important condition is to have someone who is willing to lead the meeting. For the last few meetings, it was Barry McFarland, and he gave a series of talks on quantum entanglement and entanglement entropy. Before this, we had a series of talks on the interior of black holes. We had a series of talks on symmetries and the role they play in physics, basically representation of Lie algebras and how they lead to quarks and omega minus and so on. And for next week, if Barry is willing to lead another session related to quantum entanglement and entanglement entropy, this would be great. If not, plan B, I would probably lead a session on Gissing's view that real numbers are not real in the sense that they are the wrong choice for physics. And he proposes the use of, I think it's called intuitive or intuitionist mathematics that's about 100 years old for physics.
Yeah,
okay.
That's cool. I like that.
Yeah.
Is it a huge group?
What?
Is it a very large group, or it's like a different field?
Usually we get about, on Zoom, we get about a dozen people.
Oh, okay.
A dozen people, maybe a little bit more. When we met in person, it was very limited because the last location where we met was at the Science Library in Midtown Manhattan, where we could not have more than 6 people in the room.
Oh.
So sometimes we cheated, we had 7 or 8, but we were not allowed to have more than 6.
Yeah, this Zoom thing, I know people get tired of it, but I think this is great. You guys are in different
it really opens
cities.
it up.
Yeah, that's right.
It's facilitating communication.
That's right.
Right?
Yeah.
Facilitating exchange.
So I like this plan of I'll move the Brooklyn to Saturday, and then we can all have a whole quantum.
What is I'll go with it because I think this is a really cool thing, but it's not my first choice, but I'll go with it. Just curious. So the Sunday Manhattan socialite quantum meetup, that's what hours? Just do they physically overlap?
It's at 1 o'clock. So 1 o'clock, in principle, it goes on for 2 hours, but just like this meeting, it goes on for maybe another hour or more.
Right. Okay.
People just keep talking.
Okay. And so you have quantum mechanics all weekend okay. And do they meet every weekend or every other? Or?
Usually every weekend.
Every weekend. Okay.
And let me tell you, for me, this is a lifesaver because until the virus came along, I used to go about twice a week to New York University for the colloquial and seminars in physics, once a week to the Simons Foundation. And this was part of my routine. And now it's out.
Yeah.
So at least we have the Zoom meetings. I would like to attend as many as possible.
Amen to that.
Yeah.
Yeah, I missed the
So,
library.
well, anyways, Matthew, really appreciate it. Thank you very much for the.
Thank you
this
for
meeting.
coming. Great to have
It was
you.
very interesting. Yeah, my pleasure. And we'll keep in touch.
Yeah.
Okay, bye, guys.
See
Bye.
ya.
Bye.
Yeah, I mean, for that matter, we should all probably wrap up soon.
Yeah.
Got some dinner waiting for me. But I'll say, you know, I didn't end up showing you like one of the last like visualizations. I'll save, you know, the full story on it for next time, but just for the sake of the flavor, you can basically, there's this very sort of elaborate program where you can create a universe full of some stuff, right? So I create a universe with a clock, 2 spins, and a harmonic oscillator. And then, you know, they're in this 0 energy state. And then I can be like, oh, let me project, you know, this clock into all of its time states and look at how the rest of the universe is steered. Or I can, you know, look at, you know, the states. I can pretend, you know, this spin is the clock, or maybe I'll have, oh shit, sorry. Sometimes if I press the buttons too quickly, it fucks up. Yeah, so you can even do like conditional measurements. So like, for example, I can be like, all right, let's say we're at the, you know, this moment in time with reference to this clock, but then I'll click this thing and be like, okay, I want the, if I want to regard the second spin as a clock and I want it to be like that moment, you know, then what are the states that this spin and that oscillator are steered to due to the entanglement? You know, you can just sort of play around with this and see, you know, what happens when you put different kinds of systems with different Hamiltonians in a universe together. So, I mean, I'll upload the code, but we'll play around with that some more next time, and I will, yeah, as I say, talk about, yeah, some of these questions about, you know, perception. It's an interesting thing. It's like, you know, I like it in a different way than I like the other things. I mean, a lot of the stuff I've been showing you guys has the benefit of being completely definite, like just mathematical constructions, which, I mean, you can take them or leave them, but they are what they are, and you can interpret them or whatever. With regard to these questions about perception, so much less is known that, you know, it's much easier to, you know, there's some bullshit
But
about
the fuzzy
it.
area is
You know,
sort
it's
of
worth,
my motivation. I
yeah,
love
exactly. That. So
Yeah.
we gotta go there. We can't not.
Right.
So,
Matthew,
yeah,
If it weren't weird, I wouldn't be as interested.
Matthew, thank you very much.
Sure, no, thank
you're
you.
very, as always, I've only seen you twice, but you're a very animated presenter. So even though, you know, you are frequently or mostly, you know, brilliant or near brilliant when you do your presentations, the animation keeps us all awake and engaged. And
Yeah, it's contagious.
no, it really is a, you're very, very effective as a presenter. If you haven't, you know, taught at the university level, you probably should be teaching at the university.
Yeah, thank you very much for saying that. I really appreciate that. I actually, I have a master's degree in creative writing, and I taught English classes years ago. But now I'm thinking about getting a PhD in physics. And so someday maybe I will.
So you're not formally trained in physics?
I've taken classes,
certainly could
but no, I don't have a
pretty
PhD.
convincingly.
Yeah, I don't have a PhD in it.
Did you major in it?
To come. No, not even.
So just on the math even? All this was just sort of like a hobby?
Yeah, I mean, it's been many years now. But yeah, no, I mean, taught myself a lot of stuff.
Well, evidently, yes, you have.
It's, you know, oh, wait, someone's coming in. What's up? Oh my God. Guys, look at this. Look at this dinner. This dinner was just brought to me. The generosity of Anna here is unbelievable. All right, I got to go eat this, guys. Should eat it
Enjoy.
downstairs with them.
Thanks again for everything. See you
Yeah,
next
it's
time.
been real.
Okay,
See you
man.
next time.
Thank you.
Adios.
Take care.
No, we were just actually stopping it anyway. Yeah.
Like, oh shit. Because we were eating, but then I was like, okay, like at this point, like,